On a quiet night, you step outside and look up. The sky is still, the air cool, and there it is, the moon, pale and constant, drifting silently above. Its light spills across rooftops and treetops, casting soft shadows that stretch and sway with the breeze. We have known this companion for as long as we have existed, charting our months, guiding our tides, shaping our myths. But imagine, just for a moment, that it wasn't alone. Imagine another moon sharing that sky, its glow mingling with the first, weaving two rivers of light across the dark. Two orbs pulling at the oceans, at the air, at the earth itself, and perhaps at us. The nights would be different. The tides would dance to a stranger rhythm. Our history, our science, even our stories might have taken another path entirely. What would such a world feel like? How would it change the planet we know, the life we are part of, the way we see ourselves beneath the stars? Tonight, we'll wander through that possibility, step by step, from the earliest days of the Earth to the far future we can only guess at. This is Arcane Skies. If you enjoy traveling through these questions with us, consider subscribing, leaving a like, and sharing where and when you're listening from. We'll meet you there, under the same sky. Around 4.5 billion years ago, the young solar system was a chaotic painting of dust, gas, and colossal rocks colliding without pause. Earth at that time was only a half-finished world, its outer shell a molten ocean of magma, wrapped in a dense primordial atmosphere thick with water vapor, methane, and carbon dioxide. Within the same orbital neighborhood, a planetary body roughly the size of Mars, which scientists today call Theia, drifted along an unstable path. The collision between Theia and Earth was not a gentle meeting of two drifting objects. It was an impact at tens of thousands of kilometers per hour, unleashing an energy so immense it vaporized much of the crust of both worlds. Debris was flung high into space, forming a glowing ring of molten rock and dust encircling the battered Earth. From that incandescent chaos, through the slow pull of gravity, our moon was born. But what if that cosmic accident had played out differently? What if, instead of merging into a single large satellite, the swirling debris had gathered into two? Imagine the moon's birth not as the creation of one sphere, but two, each large enough to claim the title of moon, each sharing the sky above a still young Earth. In some modern computer simulations, scientists have found that when impact debris spreads far enough, it is entirely possible for multiple large clumps to condense. Observations of the giant planets, Saturn, Jupiter, Uranus, show us that multiple moons are the norm, not the exception. The difference is that Earth, being smaller and lighter, would find it far more difficult to keep two large moons stable over billions of years. Still, in the right circumstances, it could happen. Picture the very first nights on such a world. Against the blackness of space, two glowing orbs, both still radiating the heat of their molten youth, circle a smoldering planet. One looms larger, the other smaller, their light shimmering over vast primeval oceans that have yet to host a single living thing. Plumes of steam rise from Earth's searing surface, forming thick, roiling clouds that occasionally part to reveal the twin spheres drifting together across the sky. It is a vision that would have staggered the imagination of any creature capable of looking upward, though in those days, no such creature existed. From a physics standpoint, the formation of two moons is far from impossible. As the impact debris began to cool and solidify, denser regions in the disk would have pulled material toward themselves. If two such dense zones formed far enough apart, each could continue to accumulate mass, eventually becoming a separate moon. In many hypothetical models, one moon would end up orbiting closer to Earth, moving faster and feeling stronger tidal forces. The other would remain farther out, orbiting more slowly. This arrangement would create an immediate gravitational puzzle. The two moons would not only orbit Earth, they would subtly tug on each other, distorting orbits and shifting speeds. Over immense spans of time, this could lead to stable patterns or to catastrophic encounters. But let us suppose they did survive, that the newborn Earth settled into a long-term partnership with two moons. The consequences would be profound. Tidal forces, the invisible handshake between ocean water and lunar gravity, would become far more complex. Instead of the relatively simple pattern of two high tides and two low tides that we know today, the interplay of two moons could produce unpredictable surges and retreats of the sea. Some tides would be higher, others lower, and the timing would vary in ways that might defy easy rhythm. Over geological timescales, this altered tidal landscape would shape the coastlines, nutrient flows, and tidal pools where early life might first take root. Entire evolutionary pathways could shift, favoring certain species while disadvantaging others, simply because the water came and went differently. Intriguingly, some scientists suspect that something like this might actually have happened, if only briefly. In 2011, researchers at the University of California proposed a model suggesting that Earth once had a second moon, much smaller than the one we see today. This smaller companion, perhaps a few hundred kilometers across, may have shared the same orbit as the main moon, but on the opposite side of Earth. For millions of years, they coexisted, until gravitational instabilities drove them together. The smaller moon slammed into the larger one in a slow, merging collision, creating the stark asymmetry we see today. One hemisphere of the moon smoother and flatter, the other rugged and heavily cratered. If this model is correct, then for a short chapter in Earth's history, our planet did indeed have two moons. And so the great question emerges. What if those moons had never collided? What if they had continued on, tracing their paths through the sky for billions of years, until humans raised their eyes to find not one familiar lantern in the night, but two? The very foundation of Earth's history would have been rewritten. Climate, tides, life, and even our sense of the cosmos would have been shaped under their twin light. All of it hinging on the smallest of changes in how the debris of a single ancient impact happened to fall back together. If Earth had been blessed, or burdened, with two moons from the earliest days, the first challenge they would face would be finding a stable arrangement in which to orbit. The universe is not kind to systems where two large satellites circle the same planet. Their combined gravitational pull creates a delicate, restless balance. Without the right conditions, they would drift toward collision, fling one another into space, or cause erratic shifts in each other's paths. But there are possible configurations where both could survive for billions of years. Astronomers have explored these through both theoretical mathematics and computer simulations, searching for the rules of coexistence in the silent geometry of the cosmos. One possibility is that the moons would orbit at different distances from Earth, each following its own path at a safe remove from the other. The inner moon, closer to Earth, would whip around in a faster orbit, completing a revolution in just a few days. The outer moon, farther away, would move more slowly, taking perhaps a month or more to complete its journey. In this arrangement, they would never overtake one another. Still, their gravitational influence would be constant, tugging subtly on Earth and on each other, shaping not only tides but also the long-term evolution of their orbits. Over millions of years, these tugs could shift distances, sometimes drawing them nearer, sometimes pushing them apart, like dancers in a slow, endless waltz. Another scenario involves something called a Trojan orbit, in which one moon follows the other at a fixed angle, 60 degrees ahead or behind, along the same orbital path. We see this in our solar system among asteroids that share Jupiter's orbit around the Sun, clustered at points called Lagrange points, where gravitational forces balance just enough to hold them in place. If one of Earth's moons occupied such a position relative to the other, they could theoretically remain locked in this arrangement for extraordinary spans of time. In this case, from any single point on Earth, you might see the larger moon rise in the east, while the smaller one remained invisible behind the planet. And only weeks later would it appear, trailing after its companion across the night sky. There is also the possibility of a resonant orbit, where the moon's paths are not identical, but linked by a simple numerical ratio. For example, the inner moon completing 2 orbits in the same time it takes the outer moon to complete 1. This kind of resonance exists among the Galilean moons of Jupiter, where Io, Europa, and Ganymede follow an intricate dance that keeps them from colliding while locking them into a repeating rhythm. For Earth, such a resonance could create a predictable, almost musical relationship between the moons, but one that would still produce tides far more complex than the gentle pulse we know today. The immediate effect of having 2 moons would be felt in the oceans. The gravitational pull of each moon would create its own tidal bulge on the side of Earth nearest to it, and a secondary bulge on the far side. Depending on their positions, these bulges could amplify one another, producing extreme high tides, or they could partially cancel out, creating unusually low tides. The timing of these events would shift constantly as the moons moved through their orbits, leading to a tidal calendar that no simple pattern could predict. For ancient life forms, this might have been an engine of diversity, forcing coastal organisms to adapt to a broader range of water levels, salinities, and exposure times. Some species might thrive in the extreme highs, others in the long, shallow ebbs, creating an ever-shifting mosaic of habitats. From the standpoint of Earth's rotation and axial tilt, the story grows even more intriguing. Our single moon plays a crucial role in stabilizing Earth's tilt at roughly 23.5 degrees, which governs the rhythm of our seasons. Without the moon, Earth's axis might wobble wildly over millions of years, leading to dramatic climate swings. With 2 moons, the stabilizing effect could be stronger, or it could become destabilizing, depending on the moon's masses and distances. In some models, 2 moons of unequal size could produce competing gravitational influences, slowly pulling the axis in slightly different directions. Over time, this might lead to small but measurable shifts in climate zones, subtly altering rainfall patterns, ice coverage, and the distribution of life across the planet. The sky itself would be transformed into a stage of shifting beauty. On certain nights, both moons might rise together, casting overlapping shadows and painting the landscape in twin shades of silver. On others, one might rise just as the other sets, ensuring that the night was never truly dark. Lunar eclipses could become doubly spectacular. The shadow of one moon passing across the other, visible as a faint ghostly bite taken from its glowing face, or both moons plunging into Earth's shadow in quick succession, leaving the sky for a moment lit only by the stars. And when the two lined up perfectly from Earth's perspective, the smaller might transit across the face of the larger, a slow black dot crawling across a silver disk. The interplay of light and shadow would not only shape human perception, it could influence the evolution of nocturnal creatures. On a two-moon Earth, darkness might be rarer, pushing night-adapted species to develop sharper camouflage, keener senses, or different hunting strategies. Migratory patterns, too, could change, with animals timing their movements to avoid or exploit the bright nights when predators could see more easily. Culturally, the presence of two moons would seed entirely different mythologies and calendars. Early humans might have counted months not by a single lunar cycle, but by the complex interplay between the cycles of two moons, perhaps creating great months, marked by their alignments, or naming seasons after the periods when both shone together in the sky. Stone circles and ancient monuments could have been built not to track the solstices or the full moon alone, but to chart the moments when both moons appeared in specific positions. Yet all of these scenarios depend on one central truth. Stability in celestial mechanics is rare and fragile. In the majority of simulated cases, two large moons around a planet like Earth eventually lead to disruption, the smaller being flung into space or spiraling inward to collide with either Earth or its sibling. If such a system did survive, it would be the product of a near-perfect balance achieved in the very first moments after the Theia impact. And that is perhaps the most haunting part of the thought experiment. The realization that the difference between our one-moon reality and a two-moon Earth might have been decided in just a few hours of swirling molten rock billions of years ago. The gravitational influence of the moon on Earth is one of the most quietly powerful forces shaping our world. It is the moon's pull that draws the ocean into vast, slow swells that sweep around the planet each day, creating the tides that have governed shorelines, influenced weather, and guided the biological rhythms of countless species for billions of years. With two moons, that influence would double in complexity. The tides would no longer follow a relatively smooth, predictable rise and fall. Instead, they would become a restless pattern, shifting in both magnitude and timing depending on the positions of the moons relative to each other and to Earth. Consider a day when both moons lined up on the same side of the planet. Their combined gravitational pull would stretch the oceans into a towering bulge, perhaps several times higher than the highest tides we know today. Low-lying coastal areas would be inundated more frequently, and in extreme cases, entire ecosystems could vanish beneath the water for days. In contrast, when the moons stood on opposite sides of Earth, their pulls could partially cancel each other, resulting in unusually weak tides. Between these extremes would lie countless variations, as the moons drifted through their orbits and their gravitational signatures overlapped in endlessly shifting patterns. For marine life, this unpredictability would be both a challenge and an opportunity. On our one-moon Earth, many coastal organisms live in sync with the tide. Crabs emerge to feed when the water retreats. Certain fish spawn during the highest spring tides, and intertidal plants time their growth cycles to match the rhythm of immersion and exposure. With two moons, that rhythm would fracture into multiple overlapping cycles. Species might need to evolve more flexible behaviors, responding to environmental cues on shorter notice. The constant reshaping of tidal zones would create a patchwork of habitats. Some flooded more often, others exposed for longer periods, fostering biodiversity in ways our Earth has never seen. In the earliest days of life on such a planet, the tidal zones could become an even more potent cradle for evolution. Many scientists believe that life's first steps from sea to land were taken in the intertidal pools, where water would trap microorganisms and expose them to concentrated nutrients, fluctuating temperatures, and cycles of wet and dry. On a two-moon Earth, the variety of these pools would explode, offering more evolutionary experiments for nature to run. Some pools might remain warm and shallow for days. Others might be refreshed by strong surges twice in a single night. This constant variation could speed the development of new adaptations, thicker cell walls, primitive limbs, or early respiratory systems, potentially altering the timeline of evolution itself. The moon's gravitational pull would not only sculpt the seas, it would subtly affect the solid Earth as well. Just as ocean water bulges under lunar gravity, so too does the planet's crust, rising and falling by a few centimeters each day in what scientists call Earth tides. With two moons, the crust's daily flexing could be stronger and more complex. Over geological timescales, this could influence the movement of tectonic plates, potentially increasing volcanic activity or earthquake frequency in certain regions. Imagine a world where coastal cities not only contend with extreme tides, but also live under the periodic threat of moon-driven seismic unrest. Weather patterns, too, could shift under the influence of two moons. The ocean is the engine of Earth's climate, and the tides are part of the machinery that moves heat, salt, and nutrients through its vast conveyor belts of current. Stronger and more irregular tides could accelerate the mixing of warm and cold waters, altering storm formation and precipitation patterns. Some regions might receive more frequent rainfall, while others could face prolonged droughts, depending on how the altered ocean currents redistributed heat around the globe. Seasonal monsoons could intensify. Hurricanes might follow new tracks, and the boundaries between climate zones could blur. In the human imagination, such a sky would be a constant source of wonder and perhaps unease. On bright nights when both moons were full and close together in the sky, their combined light could rival twilight, turning night into a pale version of day. Farmers might be able to work in the fields long after sunset, guided by a glow that cast sharp twin shadows. Artists, storytellers, and shamans would weave the double moons into myths, perhaps as siblings, lovers, or eternal rivals locked in their heavenly dance. In many ancient cultures, the moon was tied to the cycles of fertility and harvest. With two moons, the symbolic and spiritual associations could be doubled, intertwined into more elaborate systems of belief. But human society would also have to contend with the practical realities of such a world. Navigation by the stars might become more complicated when bright moonlight often washed out the fainter constellations. Early calendars would be more intricate, tracking not one cycle of phases, but two, along with the times when their alignments produced especially high or low tides. Coastal settlements might need to be built on higher ground to survive the periodic super tides caused by the moon's combined pull. Fishing traditions could evolve to match the moon's patterns, with some catches possible only under specific tidal conditions that returned irregularly. One fascinating possibility is that the moons themselves might not remain static in size or appearance. Over billions of years, tidal interactions transfer energy between a planet and its moons, causing them to drift outward. On our Earth, the moon is receding at about 3.8 centimeters per year. With two moons, the rate of drift could differ for each, depending on their mass and distance, leading to slow changes in their apparent size in the sky. Future generations might live in an era when the smaller moon appeared to shrink into a distant point of light, while the larger loomed ever more dominant, subtly reshaping the balance of cultural and environmental influence between them. In this imagined world, the gravitational forces that seem so abstract in equations would become tangible parts of daily life. They would be visible in the rhythm of the waves, the tilt of the seasons, the rise and fall of the land itself. And they would remind every observer, from the first primitive creature crawling out of the tide to the modern astronomer peering through a telescope, that the shape of life on Earth is written not just in the soil beneath our feet, but in the silent, ceaseless pull of the sky above. The climate of Earth, as stable as it seems over human lifetimes, is a fragile balancing act. It is shaped by the tilt of our planet's axis, the distribution of continents and oceans, the composition of the atmosphere, and the vast, subtle cycles of celestial mechanics. Among these, the tilt, our axial inclination of roughly 23.5 degrees, is one of the most crucial. It is what gives us our seasons, the slow lean toward the sun in summer and the gentle bow away in winter. Without the moon, Earth's tilt could wander chaotically over millions of years, lurching between extremes that might plunge the poles into eternal ice or scorch the tropics into barren deserts. With one moon, we enjoy a rare degree of stability. But with two moons, the picture becomes far more complex. The gravitational forces of two large satellites would not simply double the stabilizing effect. They could either strengthen it or undermine it, depending on their sizes, masses, and distances from Earth. If the moons were close in mass and placed in carefully balanced orbits, their combined influence might anchor Earth's tilt more firmly than ever before. Our planet could enjoy tens or hundreds of millions of years of steady seasonal patterns, a gift to the slow, patient work of evolution. But if the moons were mismatched in size or moved in orbits that brought them into periodic gravitational resonance with each other, they might instead introduce small wobbles into Earth's spin, wobbles that could, over geologic time, grow into dramatic swings. These axial shifts, even if only a few degrees, could profoundly reshape climate zones. A tilt increase of just 2 or 3 degrees would lengthen summers and intensify winters in temperate regions, while shrinking the stable zones near the equator. A tilt decrease would do the opposite, flattening seasonal differences but expanding the tropics. In either case, the living world would be forced to adapt. Migration patterns could shift. Ice sheets might grow or shrink. Rain belts could move hundreds of kilometers from where they once nourished grasslands and forests. In the deep past of a two-moon Earth, these shifts could trigger evolutionary bursts, mass migrations, or even extinctions. The oceans would respond as well. Earth's great conveyor belts of current, the slow, looping streams that carry warm water toward the poles and cold water toward the equator, are driven partly by winds and partly by the distribution of solar heat, which is set by the planet's tilt. A more stable tilt could lock these patterns in place for eons, leading to a climate that, while predictable, might lack the bursts of change that have so often opened new evolutionary niches on our one-moon Earth. Conversely, a less stable tilt might repeatedly reset ocean circulation, alternately bringing life to some regions and starving others of nutrients. The moons themselves would not remain fixed in their orbits. Over time, tidal forces act like an invisible brake on a planet's rotation, transferring rotational energy into the moon's orbital motion and slowly push them farther away. Our single moon, as it drifts outward at nearly 4 centimeters per year, subtly lengthens the day. With two moons, this process could unfold at different rates for each, their outward journeys driven by the specific tidal patterns they create. If one moon retreated faster than the other, the gravitational relationship between them could shift, sometimes settling into a new balance, sometimes destabilizing entirely. A destabilized moon might begin to drift erratically, its orbit growing more elliptical. Such changes could feed back into Earth's climate by altering the tidal cycles, the distribution of sunlight, and even the amount of reflected moonlight reaching the surface. In extreme cases, a moon might be nudged toward a collision course with its sibling, or with Earth itself, in events that could unleash apocalyptic consequences. A massive impact from a moon-sized object would strip away atmosphere, boil oceans, and reset the clock on complex life. Even without such catastrophes, the interplay of two moons could produce subtler, but still dramatic, climatic effects. One possibility is the creation of long-period cycles in which the moon's gravitational pulls combine to slowly shift Earth's orbital eccentricity, the degree to which our path around the Sun is stretched into an oval. This is part of the real-world Milankovitch cycles that drive ice ages on our one-moon Earth. On a two-moon planet, these cycles could be amplified, shortened, or even overlapped with entirely new rhythms, producing a climate history with more frequent and unpredictable glacial periods. From a human perspective, such variability could be both a curse and a challenge to ingenuity. Agricultural societies might be forced to adapt to shifting rainfall and temperature regimes on timescales shorter than the rise and fall of civilizations. In a world of frequent, small axial wobbles, the norm of climate could be an illusion. Farmers might plant crops under one set of seasonal expectations, only to find them overturned within a few centuries. Ancient engineers might study the positions and movements of the moons, not merely for religious or poetic inspiration, but as vital tools for predicting floods, droughts, and growing seasons. For early astronomers, charting the motions of two moons would be an intellectual challenge, unlike anything in our own history. Predicting lunar eclipses would require complex calculations centuries before the development of formal mathematics, capable of handling them. Calendars would likely evolve to track not just the phases of each moon, but the shifting intervals when they aligned in the sky, moments that might come to define ceremonial events or political authority. The very act of timekeeping could be deeply intertwined with celestial mechanics, binding human culture even more tightly to the movements above. And yet, beneath all this complexity, there would remain a deeper truth. The climate and orbital stability of a two-moon Earth would be the product of a chance arrangement set in motion billions of years ago. A slightly different angle in the Theia impact, a slightly different distribution of debris, and the entire history of the planet could be rewritten. The fact that our real Earth enjoys a relatively stable climate for millions of years at a stretch is a rare gift, one that may not be shared by many worlds in the galaxy. A two-moon Earth might be more beautiful, more dramatic, but also more restless. Its climate a shifting tapestry woven by the unceasing pull of twin companions in the sky. In the silence of space, stability is the exception, not the rule. And perhaps that is the most striking part of imagining this world. The recognition that the fate of seas, forests, ice caps, and civilizations could hang on the fragile balance of three bodies locked together in an eternal gravitational embrace. Earth's orbit around the Sun is a path traced with precision, yet influenced by countless subtle forces. The presence of our single moon contributes to the stability of that path, not by moving Earth itself in any significant way, but by controlling the behavior of our planet's spin. The moon's gravitational pull damps down wild wobbles of our axis, helping to maintain a steady tilt over millions of years. This steady tilt gives us relatively stable seasons and reduces the likelihood of extreme, rapid climate shifts. If we were to add a second moon into this system, the stability equation would change, and not necessarily in a predictable direction. The core of the issue lies in what astronomers call gravitational torque. Each moon would exert its own pull on Earth's equatorial bulge, attempting to align the planet's spin axis with the plane of its orbit around the Sun. With one moon, this torque is relatively simple to calculate and predict. With two moons, the torques would interact, sometimes reinforcing each other, sometimes opposing each other. Over short timescales, years, decades, even centuries, these effects might be imperceptible. But over geological timescales of millions or billions of years, small differences could accumulate, altering the stability of Earth's tilt. One possible outcome is enhanced stability. If the two moons were positioned in such a way that their gravitational pulls complemented each other, they could lock Earth's tilt into an even tighter range than our single moon does now. In this case, Earth's climate could become more regular and predictable, with smaller swings between glacial and interglacial periods. Such stability might allow certain ecosystems to thrive for far longer without major disruption, fostering evolutionary continuity. However, the opposite scenario is just as plausible. If the moon's torques competed, their tug-of-war over the spin axis could create slow oscillations or precessions that are larger and more erratic than the ones we experience today. Over time, these oscillations could combine with natural variations in Earth's orbit, such as changes in eccentricity and obliquity, to produce climatic chaos. The planet could be nudged into cycles of more frequent ice ages, or into long, warm intervals that melt polar ice completely, raising sea levels and reshaping coastlines. The gravitational interactions between the moons themselves add another layer of complexity. Moons in proximity do not simply ignore each other. They exchange angular momentum, subtly adjusting each other's speeds and distances from the planet. In a stable configuration, this exchange could be periodic and harmless. But in a marginally stable configuration, these exchanges could slowly shift the moons into resonances, orbital relationships where their periods of revolution form simple ratios, like 2:1 or 3:2. Resonances are double-edged swords. They can stabilize systems for immense lengths of time, or they can amplify small disturbances until orbits change dramatically. If a resonance caused one moon to migrate outward faster than expected, its gravitational influence on Earth's spin would weaken, leaving the other moon dominant. This imbalance could lead to shifts in axial tilt, or even destabilize the resonance itself. If the resonance broke suddenly, one moon might be flung into a higher orbit, escape entirely, or spiral inward toward Earth. An inward spiral could end in a cataclysmic collision, releasing enough energy to devastate life on a planetary scale. Even without catastrophic events, the constant interplay of forces could make Earth's day length more variable over long spans of time. Our single moon is slowly lengthening the day by about 1.7 milliseconds per century. With two moons, the combined tidal braking effect could accelerate this process. Days might grow noticeably longer over hundreds of millions of years, with implications for everything from atmospheric circulation to biological rhythms. Plants, for example, are finely tuned to cycles of light and dark. A gradual shift toward longer days could alter photosynthesis patterns, crop yields, and the balance between night-active and day-active species. The path of Earth around the Sun could also feel indirect effects from a two-moon system. While the moon's masses are tiny compared to Earth's, their combined gravitational influence could cause slight but measurable oscillations in Earth's orbit. These oscillations, or perturbations, could subtly shift the timing and intensity of seasons. Over tens of millions of years, even these small changes could leave fingerprints in the geological record, in layers of sediment, growth rings in ancient corals, and the isotopic composition of ice cores. From the point of view of early human civilizations, these long-term variations would be invisible. But the more immediate, observable aspects of orbital stability, such as the predictable return of seasons, eclipses, and lunar alignments, would have been crucial to developing agriculture and navigation. If two moons altered the timing of seasonal changes even slightly, ancient societies might have been forced to build more sophisticated observational systems far earlier in history. Stone monuments, astronomical towers, and calendar systems could have emerged not just as cultural expressions, but as survival tools. In the night sky, the orbital dynamics of two moons would occasionally play out in spectacular ways. There might be periods when the moon's relative positions remained fixed for decades, followed by centuries of slow drift as one gradually pulled ahead of the other. From Earth, this could create epochs where both moons rose together in the same part of the sky, then later eras where they were rarely seen together at all. Such cycles would almost certainly be woven into the mythologies of different cultures, inspiring stories of unity, separation, and reunion. The question of stability extends beyond the mechanical. It touches the deeper idea of what kind of world could have produced humanity. Our single moon may have given us just the right balance of tidal influence, axial stability, and orbital predictability for complex life to emerge and flourish. In a two-moon world, that balance would be altered. The planet might have been more fertile and diverse, or it might have been too volatile, with climates shifting too quickly for complex ecosystems to stabilize. Perhaps intelligent life would still have emerged, but under a sky that told a different story each night. Ultimately, the stability of a two-moon Earth would depend on a delicate harmony set in motion in the aftermath of a single colossal impact billions of years ago. If the debris had coalesced into two satellites with the right masses, distances, and orbital relationships, they might have endured together until now, guiding our planet with twin hands across the eons. If not, the system would have unraveled long ago, leaving either one moon, as in our reality, or none at all. In that sense, imagining this alternate history is less about rewriting the past and more about appreciating the improbable balance that shapes the present. The human experience of the night sky has always been shaped by the moon. Its glow has lit our paths, marked our calendars, and inspired stories for as long as our species has looked upward. Imagine, then, the transformation if the sky had always held two moons. The familiar balance of light and darkness would be replaced by a layered interplay of twin celestial lanterns, their shapes shifting and trading places in a slow, eternal dance. Nights would no longer be uniform. Some would be drenched in light so bright it would seem like dusk, while others would carry strange contrasts. One moon shining full and luminous, while the other waned into a slender crescent, each casting a distinct shadow in a different direction. On nights when both moons were full, the combined brightness would rival that of an overcast day. Landscapes would be etched in sharp relief, with deep black shadows edged by pale silver light. Every object would have two shadows, overlapping in strange geometries. Rivers and seas would glisten more vividly, their surfaces catching reflections from both directions at once. Even the air itself might seem altered, filled with a cool, twin-hued luminescence. Under such conditions, nocturnal predators could see with unusual clarity, and prey animals might alter their habits, hiding more carefully or shifting their activity to nights when the moons were smaller or farther apart in the sky. There would also be nights of dramatic asymmetry. Imagine standing in a meadow at midnight, one moon looming large and low on the horizon, casting a warm amber glow through the haze, while the other, high overhead, shone cold and white. The two colors of light would mingle on the ground, creating subtle, shifting tones as clouds passed, or as the moons moved across the sky. This interplay of light would be a constant companion to life, affecting not only animal behavior, but also the way humans perceived their world. Artists might try to capture the subtle shifts in color and shadow. Storytellers might weave the differences into myths about the moods or powers of each moon. Celestial events would be more frequent and varied. Lunar eclipses could occur in quick succession, one moon passing into Earth's shadow only days before or after the other. Sometimes, both might be eclipsed in the same night, a spectacle of rare beauty, with two glowing disks fading into coppery darkness together. There could be transits, too, the smaller moon crossing in front of the larger as seen from Earth, appearing as a dark dot sliding slowly across its glowing sibling. Such events would become cultural milestones, perhaps recorded on stone, celebrated with rituals, and remembered in oral histories for generations. The motion of two moons would add a layer of complexity to timekeeping. Early human societies learned to measure months by the moon's phases. With two moons, each with its own cycle, a purely lunar calendar would have to account for the interplay of two rhythms. There would be times when both moons reached full phase together, perhaps marking the start of special seasons or festivals, and other times when their cycles were out of step, creating long intervals without this alignment. Cultures might divide the year not into months, but into periods defined by the relationship between the moon's phases, the twin full, the opposing crescents, the single reign when only one moon was bright enough to dominate the night. For navigators, the additional moonlight could be both a gift and a complication. At sea, sailors often used the stars for guidance, but the brightness of two moons could wash out the fainter constellations, limiting the number of nights when navigation by starlight was practical. On the other hand, brighter nights would make it easier to spot hazards in the water or to read the shape of coastlines. Traders and explorers might plan their voyages to take advantage of long stretches of twin moon brightness, while avoiding times when one or both moons were absent from the night sky. Human settlements would be shaped by this light as well. On a two-moon Earth, the concept of true darkness might be rare. Nights bright enough to work the fields, hunt, or travel without firelight would be common, especially in the eras before artificial lighting. Villages might be built with open courtyards designed to take advantage of moonlit nights, and architecture might incorporate patterns that played with the dual shadows cast by the moons. The cultural association between the moon and nighttime rest might be weaker, as many activities could continue under the bright silver of two full disks. Religious and mythological systems would naturally reflect the dual presence. Where our real-world myths often personify the moon as a singular deity, a goddess, a hunter, a guardian, a two-moon world might produce paired deities, twins in constant motion, each embodying different aspects of life. One might be associated with abundance, fertility, and nurturing light. The other with change, endings, or the mysteries of darkness. Stories might speak of the moons as lovers who sometimes meet, sometimes drift apart, as rivals locked in a slow race, or as parent and child, the smaller forever following in the larger's wake. The perception of time itself might be more fluid in such a culture. Instead of weeks and months tied to a single cycle, people might live by a pattern of double rhythms, always aware of where each moon was in its journey. The overlapping cycles could serve as a kind of natural cosmic clock, with rare alignments marking not just festivals, but political or spiritual turning points. Leaders might claim authority based on their birth under specific moon alignments. Wars or treaties could be timed to coincide with auspicious twin phases. For the sciences, the challenge of understanding two moons would spur earlier advances in astronomy. Predicting the positions of both would require detailed observation and careful record-keeping. Over centuries, this could lead to the development of mathematical models capable of accounting for their interactions, knowledge that might eventually extend to the understanding of planets, stars, and the wider universe. The act of studying the moons could accelerate the birth of science itself. Yet, perhaps the most profound effect would be psychological. To live under two moons would be to live with a constant reminder of complexity and balance. The sky would tell a story every night, of partnership, of change, of cycles within cycles. It might instill in people a greater awareness of interconnectedness, of how multiple forces can act together to shape the world. For all its beauty, such a sky might also carry an undercurrent of tension, a reminder that the balance is fragile and could be broken. In this imagined world, the two moons would be more than mere companions in the sky. They would be woven into every aspect of life, into the tides that shape the coasts, the rhythms that guide work and rest, the stories that define identity, and the science that seeks to understand the universe. They would be ever-present, silent witnesses to the unfolding of history, their dance above mirrored in the lives below. The pull of the moon on Earth is not limited to the oceans. Beneath the waves, beneath the continents, even deep in the mantle, the planet itself bends and flexes in response to lunar gravity. These deformations, called solid Earth tides, are small in magnitude, usually just a few centimeters of vertical movement in the crust, but their effects accumulate over time. With two moons, this constant bending would become more complicated, and in many cases, more intense. The crust and mantle would rise and fall under overlapping gravitational patterns, each moon creating its own cycle of stress and release. On our one-moon Earth, the daily tidal flexing subtly influences the motion of tectonic plates. In areas where plates are already under stress, the additional nudge from tidal forces can sometimes trigger earthquakes or affect volcanic eruptions. With two moons, there would be more frequent instances when these stresses align, amplifying each other. Imagine the gravitational pulls of both moons coinciding in such a way that the crust is stretched more than usual, the equivalent of twisting a spring to its breaking point. In fault zones like the Pacific Ring of Fire, this could lead to a higher frequency of seismic events. Volcanic activity might also be more dynamic on a two-moon Earth. Volcanism is driven primarily by heat from Earth's interior, but the movement of magma toward the surface can be encouraged or hindered by tidal stresses. When both moons exert their maximum pull, they could slightly lower the pressure on magma chambers beneath certain regions, making it easier for molten rock to rise. Over millions of years, this might result in more frequent eruptions, the creation of additional volcanic islands, and perhaps the acceleration of geological processes that reshape coastlines and mountain ranges. This interplay between tidal forces and tectonics would also influence the rate at which continents drift. Plate movement is powered by convection currents in the mantle, slow, rolling motions of heated rock. The added flexing from two moons could stir these currents more vigorously in some regions, potentially changing the pace and direction of continental drift. Over geological timescales, the arrangement of continents would determine the flow of ocean currents, which in turn would affect global climate patterns. A two-moon Earth might experience more frequent supercontinent cycles, with land masses coming together and breaking apart on shorter intervals than in our own history. Coastal geology would be especially transformed. Higher and more irregular tides would produce stronger erosion in some areas and heavier sediment deposition in others. Cliffs might be worn away faster, estuaries could expand or vanish, and new tidal flats could emerge where none existed before. These changes would constantly redraw the boundary between land and sea, forcing both human and animal populations to adapt. Archaeological records on a two-moon Earth might show a much more dynamic coastline, with ancient settlements frequently abandoned or rebuilt farther inland. The tidal power available from two moons would also be enormous. In our world, the movement of tides transfers energy from Earth's rotation into the moon's orbital motion, slowly pushing it away. With two moons, the combined tidal braking would slow Earth's rotation more quickly. This could lead to a noticeable lengthening of the day over geologic time, perhaps by several hours compared to our current 24-hour cycle, which would have subtle but far-reaching effects on wind patterns, weather systems, and the biological clocks of all living things. Geological records could bear the marks of this two-moon influence. Layers of volcanic ash in ancient sediments might reveal rhythmic patterns corresponding to specific moon alignments. Fossilized coral reefs, which grow in response to sunlight cycles and tidal rhythms, could display growth patterns far more complex than those seen today, recording the interference patterns of two lunar cycles. Even ice cores might preserve evidence of climate changes linked to the moon's combined gravitational effects on ocean circulation and volcanic activity. For early human societies, the geological consequences of two moons would not be understood in scientific terms, but their impact would be felt. Communities might live in the shadow of more active volcanoes, facing both fertile soils from ash deposits and the danger of sudden destruction. Earthquakes could occur in unusual patterns, with certain alignments of the moons becoming ominous omens. Myths might emerge of the moons, pulling at the bones of the earth, awakening mountains or shaking the ground when they drew too close together in the sky. Over millennia, the presence of two moons could even influence the distribution of natural resources. More frequent volcanic activity would produce richer deposits of minerals and ores in some regions, while shifting coastlines could create new fisheries or expose valuable deposits of salt, clay, and rare earths. Civilizations might rise and fall in part based on their ability to harness these changing resources. A harbor rich with fish under one tidal cycle might vanish a century later, replaced by a shallow bay or a stretch of salt marsh. There would be a profound feedback loop between geology and life. Active tectonics and volcanism help recycle carbon and other essential elements, maintaining a habitable climate over long time scales. If two moons intensified these processes, Earth might be more resilient to certain kinds of climate change. On the other hand, the increased geological instability could periodically disrupt ecosystems, driving rapid evolutionary change. Mass extinctions could occur more frequently, but so could bursts of diversification afterward, as surviving species adapted to altered landscapes and climates. In imagining this world, one sees a planet in constant motion, not just in the grand sweep of continents and seas, but in the daily flexing of its skin and bones under the push and pull of two companions in the sky. The land would rise and fall, the coasts would advance and retreat, and mountains would grow and crumble under a rhythm dictated not by the slow churn of the mantle alone, but by the celestial choreography overhead. Life on such a world would be shaped not only by the sun and the seasons, but by the ever-changing dance of two moons whose invisible hands could shake the ground as surely as they stirred the sea. Life on Earth has never existed in isolation from the forces of the sky. The pull of the moon, subtle yet unceasing, has been a quiet architect of the biosphere. It shapes the tides, which in turn shape coastlines, nutrient flows, and habitats. On a two-moon Earth, this architectural role would be magnified and made more intricate. The very first stirrings of life might have unfolded differently, and the path from single-celled organisms to complex creatures could have taken an altered route, perhaps faster in some respects, slower in others. In the beginning, before life had spread across the oceans, there were tidal pools, shallow basins along the early coasts that filled with seawater and then emptied again under the influence of the moon. These pools concentrated organic molecules, creating chemical environments that fluctuated in temperature, salinity, and nutrient levels. Many scientists believe such places could have been crucibles for life, providing the necessary variety of conditions for molecules to assemble into self-replicating forms. With two moons, the range of these conditions would be even greater. Imagine a coastline where tidal pools are not refreshed by a single predictable rhythm, but by overlapping cycles. Some pools might remain submerged for longer stretches when both moons' tides align, fostering slow, stable chemical processes. Others might be drained and refilled twice in a single night when the cycles are out of phase, subjecting their contents to rapid changes in temperature and chemistry. Each variation would act as a separate laboratory for evolution, testing countless combinations of environmental pressure and chemical opportunity. Over millions of years, this could yield a greater diversity of molecular structures and early life forms than on our single moon Earth. As life spread and diversified, the influence of two moons would continue. Coastal ecosystems, rich nurseries for marine life, would experience constantly shifting shorelines. Intertidal species like crabs, mollusks, and seaweeds might evolve broader tolerance ranges for salinity and moisture, able to survive both extreme high tides and prolonged low water exposure. Fish species that use tidal cues to spawn might develop more complex timing mechanisms, perhaps triggered by the gravitational patterns of both moons rather than a single lunar cycle. This could result in multiple spawning peaks throughout the year, increasing genetic variation and resilience. On land, the ripple effects of two moons would be felt through climate and resource distribution. If the moons influenced axial stability in a way that made seasons more predictable, terrestrial life might enjoy long periods of stable conditions, allowing for the evolution of large, specialized species. Conversely, if the moons caused small but frequent shifts in climate zones, life on land might evolve toward adaptability and mobility, favoring generalists over specialists. The history of life would be written in the balance between stability and change imposed by these celestial companions. In the oceans, tides play a vital role in circulating nutrients from the deep to the surface, feeding plankton blooms that form the foundation of the marine food web. With two moons, stronger and more irregular tides could enhance this vertical mixing, potentially leading to more frequent and intense blooms. This, in turn, would support larger populations of fish, seabirds, and marine mammals. Entire migratory patterns might be tied to specific tidal alignments of the moons, with whales, turtles, and seabirds timing their journeys to take advantage of rich feeding grounds exposed or replenished by certain combinations of tidal force. The moon's gravitational influence on the crust, through tidal flexing, could also shape life indirectly by affecting volcanism and tectonics. More frequent volcanic activity would not only create new land, but also release gases and minerals into the atmosphere and oceans. Volcanic islands often become biodiversity hotspots, their isolation fostering rapid speciation. On a two-moon Earth, such islands might form and disappear more often, acting as evolutionary stepping stones between continents and archipelagos. Mass extinction events could also bear the fingerprints of two moons. A combination of geological instability, stronger tidal flooding, and potential climate oscillations might periodically disrupt ecosystems on a global scale. While devastating in the short term, these events could clear ecological niches, paving the way for evolutionary innovation. The fossil record of a two-moon Earth might show sharper peaks and valleys of biodiversity, sudden losses followed by equally rapid bursts of new life. Human evolution, too, could be influenced by this double-lunar world. Our distant ancestors, living along shifting coasts and floodplains, might have developed heightened spatial awareness and adaptability to changing environments. The need to navigate a world with more complex tidal calendars could have fostered early observational skills, the ability to predict patterns in the sky, and perhaps even the beginnings of mathematics. The moons would not just be silent witnesses to human emergence. They would be active participants in shaping the intellect and culture of our species. Cultural development would be intertwined with biology. In societies that depended on fishing, hunting, or farming in tidal zones, the two moons' patterns would dictate the timing of labor, festivals, and trade. The observation of these patterns would be critical for survival, embedding astronomical knowledge deep within oral traditions. Over generations, this practical knowledge would merge with spiritual interpretations, with the moons seen as guardians of fertility, providers of abundance, or capricious forces to be appeased. Even in modern times, the biological influence of two moons would remain. Many animals, including humans, retain circadian rhythms and, in some cases, lunar rhythms that influence sleep, reproduction, and behavior. On a two-moon Earth, these rhythms could be more varied and complex. Some species might synchronize with one moon cycle, others with the other, and still others with the interference pattern of both. Scientists studying such life would need to account for multiple lunar influences, perhaps discovering biological clocks unlike anything seen on our single-moon world. In the end, the evolution of life on a two-moon Earth would be a story of expanded possibility. The greater range of environmental conditions, the increased dynamism of coasts and climates, and the interplay of geological and astronomical forces would produce a biosphere both more varied and more volatile. Life might flourish in forms and patterns we can only imagine, some more resilient to change, others more exquisitely adapted to the fleeting conditions created by the shifting dance of two moons. Long before humans built cities, carved monuments, or recorded their thoughts in writing, they were watchers of the sky. The rhythm of the sun, the stars, and especially the moon became the first great clock, marking the passage of time in a world without mechanical instruments. On our real Earth, that clock has a single hand, the solitary moon waxing and waning through its 29.5-day cycle. But on a two-moon Earth, our ancestors would have grown up beneath a more intricate clock face, one with two hands moving at different speeds, sometimes overlapping, sometimes drifting apart. This sky would have been not only a source of light and beauty, but a puzzle that demanded attention and interpretation. Imagine a group of early humans, perhaps Homo erectus or Neanderthals, gathered around a fire on the edge of a savanna. The night is bright enough to cast two overlapping shadows for each person. One moon hangs large and golden near the horizon, its reflection shimmering in a distant river, while the other, smaller and colder in hue, rides high overhead. The elders watch their positions and speak softly of when the two will next meet in the sky, an event that might be rare enough to seem sacred. Children would grow up learning not just the shapes of the moons, but their cycles, understanding instinctively that the night sky follows patterns, even if those patterns take months or years to repeat. The presence of two moons would have practical consequences, even for these early humans. Hunting strategies might be timed to phases when the nights were dark enough to conceal movement. Foragers might use the bright twin moon nights to travel longer distances without the need for firelight. The increased light could allow for nighttime gathering of edible plants or shellfish, expanding the range of productive hours each day. In harsher climates, the bright nights might even mean greater safety, as predators could be more easily spotted from a distance. Over time, observation would become tradition. Certain alignments of the moons might be associated with seasonal events. The migration of herd animals, the flowering of a particular plant, or the return of fish to spawning grounds. These associations could be passed down through generations, forming the earliest kind of lunar calendar, not based on one repeating cycle, but on the interplay of two. An alignment of both full moons might be celebrated as a time of abundance, while a rare night when both moons vanished below the horizon might be viewed as ominous, prompting rituals to ensure the return of their light. Archaeological evidence from our one-moon Earth shows that even in the Paleolithic, humans carved notches into bones or etched marks into stone to track lunar phases. On a two-moon Earth, such artifacts might be more complex, double rows of markings, or spirals intertwining to represent the cycles of each moon. A bone tool found thousands of years later might carry sequences of dots in two parallel lines, each representing a different lunar phase, with special symbols for the nights when the two moons' full phases coincided. Artistic expression would also be shaped by this duality. Cave paintings might depict animals beneath a sky with two luminous disks. Early sculptures could show human figures with twin moons hovering above their heads, perhaps as a symbol of wisdom or spiritual connection. In mythology, the moons might be cast as siblings with distinct personalities, one steady and nurturing, the other changeable and wild, whose relationship mirrored the human experience of cooperation and conflict. As human societies advanced into the Neolithic, the moons would become tools for planning agriculture. Farmers on a two-moon Earth might time planting and harvesting not just to the seasons, but to the influence of particular lunar alignments on weather and tides. Rituals to bless the fields could be tied to the nights of twin full moons, seen as moments of cosmic harmony. Likewise, certain fishing or irrigation practices might be aligned with the extreme tides caused by both moons pulling together. Navigators, too, would take note. On our Earth, Polynesian sailors used the moon along with the stars to chart their way across vast distances of ocean. On a two-moon Earth, Seafarers might develop even more sophisticated methods, learning to read the relative positions of the moons as an additional navigational aid. The brighter nights would make it easier to spot distant islands or hazards in shallow waters, extending the range of exploration and trade long before the invention of modern navigation tools. But the moons would not always be benevolent symbols. In regions prone to flooding, the extreme tides of certain alignments might bring destruction, sweeping away settlements and fields. Oral traditions could grow around these events, warning of the embrace of the moons, when both pulled the seas to their highest reach. Stories might tell of ancient villages lost beneath the water on such nights, their ruins visible only when the tide retreats under a different alignment. These tales could blend memory and myth, shaping where future generations chose to live. Over centuries, observation would evolve into science. The first astronomers would record the moon's positions on clay tablets, noting the intervals between eclipses, conjunctions, and opposition phases. Temples or megalithic structures might be aligned to mark the rising points of the moons at significant moments in their cycles. Just as Stonehenge aligns with solstices in our world, a two-moon culture might construct vast Moonhenge-like sites with multiple sightlines to track both orbits and their interactions with the sun. The intellectual challenge of predicting two moons would be immense, but the rewards would be equally great. Accurate predictions could guide agriculture, fishing, navigation, and even diplomacy, as leaders might choose auspicious alignments to begin treaties or launch campaigns. In such a world, the mastery of lunar knowledge could be as politically powerful as control over armies or resources. Yet beneath the practical uses and mythological layers, there would always remain the quiet, personal experience of the two-moon sky. For an early human lying on their back in the grass, watching the twin disks drift slowly overhead, the sight might inspire a sense of connection to something vast and enduring. For a hunter resting after a long trek, the double shadows stretching from their feet might serve as a reminder that the world is shaped by forces far beyond human control. And for a child seeing the moons align for the first time, the memory could become a lifetime's anchor, a moment when the universe seemed to move in perfect balance. In a two-moon Earth, the story of humanity would be inseparable from the story of the sky. Our ancestors would have learned its patterns before they learned to write, carried them in memory before they could carve them in stone, and woven them into every layer of culture, from survival skills to sacred rites. The moons would have been both teachers and mysteries, companions in the long journey from campfire shadows to city lights, always there, always watching, always shaping the course of human destiny. As human societies evolved from scattered tribes into the first settled communities, the sky remained a constant point of reference. In a two-moon world, this reference would be richer, more complex, and far more central to the structure of civilization. By the time the earliest city-states emerged, the movements of the two moons would already be woven into every aspect of life, from the planting of crops to the coronation of kings. The sky would not simply be observed. It would be measured, mapped, and interpreted as a kind of celestial law. In ancient Sumer, Egypt, or the Indus Valley, or their equivalents in this alternate history, priests and astronomers might spend nights atop ziggurats, temple roofs, or stone platforms, tracking the positions of both moons against the star field. Each moon would have its own name, personality, and divine associations. One might be revered as the Great Mother, guardian of fertility, agriculture, and childbirth. The other might be the Watcher or Herald, linked to omens, travel, and the cycles of trade and war. Their interactions, conjunctions, oppositions, eclipses, would be seen as divine conversations, arguments, or unions. Religion in such civilizations would be inseparable from lunar observation. Twin lunar deities could be central to state-sponsored cults, with festivals timed to their alignments. A double full moon might be celebrated as a time of harmony, marked by public feasts and ceremonial offerings. An eclipse involving both moons in quick succession could be interpreted as a cosmic warning, prompting rituals of purification or the suspension of political activity. Priests might be tasked with negotiating between the moons through offerings, ensuring that their combined influence brought prosperity rather than disaster. Architecture would reflect this dual reverence. Temples might be aligned not just to solstices or equinoxes, but to specific lunar events. The rise of one moon over a temple's main axis during a certain festival, or the alignment of both moons with a sacred gateway once every few decades. Monumental structures could feature twin towers or domes, symbolizing the two celestial rulers. Courtyards might be designed so that their shadows during particular lunar alignments fell in patterns believed to hold magical or protective power. In political life, the moons could serve as symbols of legitimacy. A ruler crowned during a rare conjunction of the two moons might be believed to rule with divine favor. Dynasties could trace their authority to such events, using them as proof of their destined right to lead. Wars might be launched under auspicious twin phases, with armies believing the moon's combined light would guide them to victory. Conversely, periods of political instability could be blamed on discord between the moons, as interpreted by court astrologers. Calendars in a two-moon civilization would be more intricate than our own lunar calendars. Instead of months defined by a single cycle, there could be great months marked by the repetition of a specific alignment between the two moons. The time between these alignments could span multiple ordinary months, creating a layered calendar system that combined short cycles, individual moons' phases, with long cycles, their relative positions. Festivals, taxes, agricultural duties, and even legal deadlines might be scheduled according to these complex patterns. Economic activity would also be tied to the moons. Merchants and sailors might plan expeditions based on the brightness and tidal effects of specific alignments. Markets might hold twin moon fairs during periods when both moons were bright and high in the sky, attracting traders from distant lands. In coastal cities, extreme tides caused by the moon's combined pull could open or close harbors, making lunar knowledge essential for shipping and fishing. Inland, farmers might rely on lunar predictions to time irrigation cycles, especially if rivers were influenced by tidal surges far upstream. In art and literature, the two moons would be an endless source of inspiration. Poets might compare lovers to the celestial pair, forever circling but rarely meeting. Dramas and epics could personify them as siblings, rivals, or star-crossed partners. Painters and sculptors might depict famous historical events under specific lunar configurations, embedding astronomical timestamps into cultural memory. Over centuries, A civilization's identity might become deeply entwined with the imagery of the twin moons, appearing on coins, seals, and banners. Trade between different regions could also be influenced by the moons. Just as ancient peoples on our Earth shared astronomical knowledge along trade routes, so too in this world would lunar cycles form part of the common intellectual currency. A merchant from one empire might recognize the significance of a lunar alignment in a foreign port, using it to gain favor or strike deals. Disputes over the correct interpretation of lunar omens could even spark diplomatic tensions, or conversely, shared reverence for a rare twin eclipse could unite rival states in temporary alliance. Not all civilizations would interpret the moons the same way. Some cultures might see them as cooperative forces, bringing balance and abundance. Others might view them as antagonists whose conflicts spill over into the mortal world. In one land, the smaller moon might be venerated for its subtlety and mystery. In another, it might be feared as a bringer of misfortune. These differences could shape alliances, wars, and cultural exchanges, making the moons as much a political factor as they were an astronomical one. As civilizations advanced, their understanding of the moons would deepen. Mathematicians and astronomers might develop models capable of predicting their positions years or decades ahead. Such predictive power would be a form of political leverage. Rulers could use it to plan festivals, time military campaigns, or impress foreign envoys. The construction of observatories would become a matter of state importance, and the role of court astronomer could carry immense influence, second only to the ruler themselves. Yet, despite these advancements, the moons would retain their power to inspire awe. Even the most learned astronomer would be humbled by the sight of both full moons rising together over the horizon, their light mingling to bathe the land in silver. Farmers, merchants, soldiers, and rulers alike would pause to watch, reminded that their lives, their fortunes, and their histories were bound to the slow, silent dance of two distant worlds. In the interplay of those two orbs, civilizations would find both a clock and a mirror, a measure of time and a reflection of their own struggles for balance, harmony, and survival. History, as we know it, is a tapestry woven from countless threads. The ambitions of rulers, the migrations of peoples, the discoveries of inventors, and the chance alignments of nature. Yet behind all these human choices lies the backdrop of the physical world: the land, the seas, the climate, and the sky. A two-moon sky would have been more than just a curiosity. It would have been a silent actor shaping the stage upon which history unfolded. Wars might have been fought under different circumstances, discoveries made sooner or later, and the very rhythm of civilizations altered by the steady, luminous presence of twin companions above. In warfare, timing has always been critical, and the moon has long been a guide for armies. On our Earth, full moons provided light for night marches or attacks, while new moons offered darkness for stealth. With two moons, commanders would face a more complex calculation. There might be few nights of complete darkness. The combined glow of even two crescents could illuminate a battlefield enough to reveal movement. This could reduce the advantage of night raids, pushing military tactics toward daylight engagements, or forcing armies to fight under a perpetual pale light. Conversely, rare alignments when both moons were absent from the sky could become coveted windows for covert action, leading generals to wait years, or even decades, for the perfect moment to strike. Naval warfare and exploration would also be transformed. The extreme tides produced by the combined pull of two moons could dictate the opening and closing of harbors, the navigability of coastal waters, and the safety of long voyages. In this world, naval powers would be those who mastered lunar prediction, using it to time blockades, invasions, and merchant convoys. Entire fleets could be trapped or freed by a few days' difference in tidal height, and great naval victories might be remembered not only for the skill of admirals, but for the favor of the moons. Exploration on a two-moon Earth might have occurred sooner and farther than in our history. The brighter nights provided by twin moons would make long-distance travel safer, allowing caravans to cross deserts or forests with less risk from predators or unseen hazards. Seafaring cultures could sail through more of the lunar month without depending entirely on starlight. This increased mobility might lead to earlier contact between distant cultures, accelerating the spread of technology, languages, and ideas. It's possible that the great ocean-crossing voyages we associate with the late medieval period could have occurred centuries earlier in this alternate timeline. The scientific revolution itself might have been shaped by this double-lunar reality. Astronomy would have been a more challenging and mathematically rich field from its earliest days, as scholars worked to model the motions of two large interacting bodies. The need to predict eclipses, conjunctions, and tidal extremes would drive advances in geometry, trigonometry, and eventually calculus. Observatories might be built centuries earlier than in our history, and the habit of precise observation, essential for the birth of modern science, could have developed more widely and deeply. This might have led to earlier breakthroughs in navigation, engineering, and even physics. Philosophy, too, would reflect the presence of two moons. Many of our real-world philosophical traditions have drawn metaphors from the singular moon, its cycle of growth and decline as a symbol of impermanence, renewal, or duality between light and darkness. In a two-moon culture, such metaphors could become more intricate. The moon's relationship, sometimes harmonious, sometimes opposed, might be seen as an emblem of balance between competing forces, order and chaos, reason and emotion, fate and free will. Philosophers could debate whether the moons act in cooperation or conflict, and whether their differing cycles reveal deeper truths about the nature of the universe. Religious and political movements might use these celestial events as turning points in history. A prophet might declare a vision during a rare triple eclipse, both moons in Earth's shadow while the sun itself is partially obscured, and such an event could galvanize a following. Empires might mark their founding dates not by the sun's position, but by a spectacular lunar alignment, embedding astronomical events into national identities. In a world where the skies provided such vivid spectacles, leaders could harness them as powerful tools of propaganda, convincing their subjects that the heavens themselves endorsed their rule. The cultural arts, poetry, music, visual design, would carry the imprint of the moons. Entire genres might emerge around lunar imagery, epics recounting historical battles fought under a blood-twin moon, folk songs about lovers separated until the next rare conjunction, and architectural styles that play with the double shadows cast by their light. Theater performances might be scheduled to coincide with certain moon phases, using the actual sky as a part of the stage. Painters and sculptors might depict the moon's shifting positions as symbolic of political or personal themes, embedding celestial cycles in the language of art. Even economic systems could evolve differently. Agriculture in many parts of the world depends on lunar calendars for planting and harvesting. With 2 moons, these calendars would be far more complex, and mastery of them could be a source of wealth and influence. Guilds of lunar keepers might arise, specialized groups responsible for maintaining accurate records of the moon's cycles and advising farmers, merchants, and governments. Control over this knowledge could be tightly guarded, making lunar prediction a matter of state security. Crucially, the shared experience of 2 moons could create a stronger sense of global connection. While cultures might interpret the moons differently, all humans would see them, track them, and depend on them. The 2 moons could become a universal language, a shared frame of reference for trade, diplomacy, and storytelling. Traveling from one side of the world to another, a merchant or pilgrim might feel a kinship with strangers simply because both could look up and recognize the same celestial pairing. Yet there is also the possibility that this celestial duality could deepen divisions. If one culture viewed a particular alignment as auspicious, while another saw it as a bad omen, such differences could fuel misunderstandings, hostility, or even conflict. Disputes over the meaning of a rare lunar event might play a role in starting wars or in sabotaging peace treaties. History would thus be shaped not just by the physical reality of 2 moons, but by the human interpretations layered upon it. Over the centuries, as knowledge advanced and science began to explain the motions of the moons in purely physical terms, their symbolic and emotional power would remain. Even in an age of telescopes, rockets, and space stations, the sight of 2 moons rising together would stir something ancient in the human mind. A reminder that our species' story has always been tied to the sky. And in this alternate history, every major event, from the rise of empires to the voyages across oceans, would carry in some quiet way the mark of the 2 moons' steady, silent presence above. 2 moons orbiting the same planet form a system of delicate complexity. From a distance, their motion might appear graceful and eternal, but beneath the beauty lies a constant negotiation of gravitational forces. Each moon is influenced not only by the Earth's pull, but also by the subtle tug of its sibling. Over days and months, these interactions might seem minor. A fractional shift in speed here, a slight nudge in position there. Yet over thousands or millions of years, such minute adjustments can accumulate, shaping the entire history of the system. At the heart of this dynamic is the concept of orbital resonance. Resonance occurs when 2 orbiting bodies settle into a simple numerical ratio in the time it takes them to complete a revolution. A 2-1 resonance, for example, means the inner moon circles Earth twice in the same time it takes the outer moon to make one trip. This pattern locks their positions into a repeating relationship, preventing close approaches and potential collisions. Many of Jupiter's moons are bound in such resonances, their motions choreographed like dancers, keeping perfect time to avoid stepping on each other's toes. For a 2-moon Earth, a stable resonance would be the best guarantee of long-term survival. If the moons fell into a 3-2, 2-1, or even 5-3 resonance, they could remain in their respective orbits for billions of years. But achieving such harmony would depend on the circumstances of their formation. If the moons emerged from the debris of a single giant impact, as in the Theia scenario, Their initial orbits might be chaotic. Some simulations suggest that multiple moonlets can form after such an impact, but over time they tend to merge into a single body or scatter into space. For two moons to persist, they would have to quickly settle into an arrangement that avoided dangerous close encounters. Even in a stable resonance, the moon's gravitational influence on each other would produce measurable effects. They could cause slight eccentricities in one another's orbits, making them slightly more oval than perfectly circular, or induce small oscillations in their orbital inclinations, tilting them relative to Earth's equator. These oscillations might be slow, taking centuries or millennia to complete a cycle, but they would be noticeable to careful observers over the course of human history. Ancient astronomers could record such long-term shifts, perhaps without fully understanding the mechanisms behind them, and fold them into elaborate predictive systems. If the moons were not in resonance, the danger of instability would grow over time. Without a stable pattern to prevent close approaches, gravitational interactions could alter their velocities just enough to cause trouble. A series of small encounters might push one moon into a higher orbit while dragging the other closer to Earth. The closer moon would then experience stronger tidal forces, which could either stabilize it in a tighter orbit or, in extreme cases, tear it apart. If a moon crossed the Roche limit, the distance within which tidal forces exceed the moon's own gravity, it could be shredded into a ring of debris, much like Saturn's rings. Such a ring might persist for millions of years, casting a pale band across the sky and reshaping Earth's tides in yet another dramatic transformation. Over time, the debris could gradually coalesce into a new moon, starting the cycle anew, or it could spiral inward and rain down on Earth as countless meteorites. The geological record would preserve such an event as a sudden spike in impacts, a layer of strange minerals spread across the globe. Collisions between the moons themselves, while rare in stable configurations, remain a possibility over astronomical timescales. A slow-motion impact between two moons would be far more catastrophic than it might sound. At orbital speeds of around 1 kilometer per second, even a gentle collision would release energy equivalent to millions of nuclear weapons. The resulting debris would range from dust to mountain-sized fragments, many of which could fall toward Earth, igniting the atmosphere and triggering mass extinctions. The surviving moon, swollen by the addition of its siblings' material, might bear a scar for the rest of its existence, much as our moon's far side is thought to have been reshaped by the accretion of a smaller companion billions of years ago. Long-term tidal evolution adds another layer of complexity. On our real Earth, the moon is slowly receding as tidal forces transfer rotational energy from the planet to the satellite's orbit. With two moons, the rate of this transfer would be divided between them, and their different masses and distances would cause them to drift outward at different speeds. If one moon receded much faster than the other, the changing ratio of their orbital periods could shift them out of resonance, destabilizing the system. Conversely, tidal interactions could gradually drive them into resonance, locking their future paths together. The presence of the Sun complicates matters further. Earth and its moons are not an isolated system. Solar gravity constantly tugs at both moons, subtly modifying their orbits. At certain distances, the Sun's influence could create resonances between a moon's orbital period around Earth and Earth's own year-long orbit around the Sun. These solar resonances can be destabilizing, gradually altering orbital eccentricities until close approaches or collisions become inevitable. Astronomers studying such a system would need to account for this three-body, or rather four-body, interaction: Earth, Moon A, Moon B, and the Sun. Over billions of years, a two-moon Earth would face three likely fates. In the most optimistic scenario, the moons would settle into a stable resonance early and remain there indefinitely, their dance preserved for as long as the sun shines. In the second scenario, gradual drift or solar perturbations would destabilize the system, causing one moon to be ejected into space, perhaps becoming a wandering body in the solar system, while the other remained. In the third and most dramatic scenario, the moons would eventually collide, creating a single, larger moon and leaving Earth's sky forever changed. The timescales for these outcomes are vast, far beyond the span of human civilization. Yet if such a system existed, humans might speculate about its future, just as we ponder the eventual death of our sun. The knowledge that one moon could be lost or destroyed might inspire both awe and anxiety, influencing cultural narratives and philosophical reflections. Would people see the moons as eternal guardians, or as fragile companions whose presence was only temporary in the grand sweep of time? In contemplating the astrophysics of two moons, one comes to appreciate the improbable stability of our own single moon. It is a reminder that celestial mechanics, for all their mathematical elegance, are subject to the same truth that governs life. Stability is rare, change is inevitable, and beauty often exists only because a set of improbable conditions happen to hold for a while. A two-moon Earth would be a living laboratory of these truths, its sky a constant performance of balance and tension. A performance whose ending might be written in the very equations that keep it alive. It begins quietly, almost imperceptibly, in the mathematics of orbital drift. For millions of years, the two moons of Earth have circled in apparent harmony, their paths kept apart by a stable resonance. But tidal forces are relentless, and the delicate balance is not immune to the slow erosion of time. One moon drifts outward slightly faster than expected. The other's orbit grows just a fraction more eccentric. The resonance slips. Their paths shift, and once in every few thousand orbits, they pass each other at a slightly smaller distance. The change is so subtle that no observer, not even the most careful ancient astronomer, would notice in a single lifetime. Yet, in the silent clockwork of the cosmos, the countdown has begun. Centuries pass. The close approaches become closer still. Gravitational tugs during each encounter alter their speeds and trajectories, feeding a slow but unstoppable spiral toward a meeting point. At last, there comes a night when the two moons rise in the same part of the sky, larger and brighter than ever before. From the surface of Earth, the view is breathtaking. The smaller moon sliding visibly against the backdrop of the larger, like two pearls drifting toward each other across a black velvet sea. Then, with a motion too slow for the human eye to register in real time, they touch. In reality, this touch is a catastrophic collision. Even at orbital speeds of just over 1 kilometer per second, the kinetic energy unleashed is beyond comprehension, equivalent to billions of the largest nuclear weapons ever built. The surface of both moons shatters in an instant, sending plumes of molten rock and vaporized dust into space. Shock waves ripple through their interiors, tearing them apart. What remains is a rapidly expanding cloud of incandescent debris, glowing red and gold in the darkness. From Earth, the night sky is transformed. For days afterward, the debris cloud reflects sunlight like a second dawn, bathing the world in eerie twilight even at midnight. Fragments of rock, some no larger than grains of sand, others the size of mountains, begin to fall toward Earth. The atmosphere ignites as the first meteors streak across the sky, producing nights of continuous fire. In the oceans, tsunamis rise from the impact of larger fragments, sweeping across coastlines with destructive force. The larger impacts penetrate deep into Earth's crust, releasing vast amounts of energy and triggering volcanic activity around the globe. Dust and ash thrown into the atmosphere block sunlight, plunging the world into a period of cooling known as an impact winter. Photosynthesis falters, food chains collapse, and many species face extinction. The oceans, too, are disrupted. Waves of heat and cold, oxygen depletion, and chemical changes ripple through marine ecosystems. The duration of this dark period depends on the volume of debris and the speed with which Earth's natural systems can clear the atmosphere. In some models, sunlight could be dimmed for years, leading to widespread crop failure and the collapse of human societies dependent on agriculture. In others, the cooling is followed by a period of rapid warming, as greenhouse gases released by massive volcanic eruptions accumulate in the atmosphere. Either way, the planet's climate enters a state of violent instability, and the survival of complex life hangs in the balance. Over decades and centuries, the debris cloud left in orbit begins to thin. Some material reaccumulates into a single, larger moon, its surface scarred and irregular, a composite of its two predecessors. This new moon would orbit farther from Earth than either of its parents, its gravitational pull slightly weaker. The tides would be reduced, the nights darker. Humanity, if it survived, would live under a simpler sky again, but a sky that carried the memory of disaster. Cultural responses to such an event would be profound. In oral traditions, the story might be told as a war between the moons, or as the death of celestial lovers. Temples could be built to honor the lost moon, and the new moon might be regarded with suspicion or reverence. The event would become a temporal anchor in history, dividing eras into before the moons fell and after. Survivors might interpret the disaster as divine punishment, a cosmic omen, or an inescapable fate written in the heavens. From a scientific perspective, the collision of two moons would be a rare opportunity to study planetary dynamics in real time. Observers with telescopes could watch the debris cloud evolve, mapping its expansion and contraction, measuring the way sunlight reflects from its particles, and tracking the reformation of a new moon. Future generations might use the evidence of this event to refine models of celestial mechanics, learning not just about their own world, but about the fates of other planetary systems. But science might come too late for the generations living through the immediate aftermath. If the impacts were severe enough, human civilization could be pushed back centuries or even millennia. Urban centers might be abandoned, populations scattered into smaller, more mobile groups. In colder regions, communities would struggle to survive prolonged winters, In warmer zones, food shortages could trigger conflict over arable land and fresh water. The disaster could act as a bottleneck in human history, reducing global population to a fraction of its former size. The biosphere, too, would be reshaped. Species unable to adapt to the new climate would vanish, while others would seize the opportunity to expand into emptied niches. Evolutionary pressures might favor hardier plants, cold-tolerant animals, and opportunistic predators. Over thousands of years, ecosystems would rebuild themselves, but they would not look the same as before. In this sense, the collision of two moons would act as both an end and a beginning, a destructive force that also clears the stage for new forms of life. In the very long term, the system might regain a kind of stability. The new moon, formed from the wreckage, would settle into an orbit determined by the distribution of surviving mass and the tidal forces of Earth and the Sun. The planet would carry the scars of the event: impact craters scattered across continents, layers of unusual rock in the geological record. But life would continue. Humanity, if still present, would tell the story to its descendants: how the sky once held two moons, how they danced together for eons, and how one day their dance ended in fire. Such an event, however catastrophic, is not purely a flight of imagination. Astronomers have observed moons and small planetary bodies in other star systems that show signs of violent collisions. Even in our own history, the asymmetry of our moon's near and far sides may be the result of a merger with a smaller companion billions of years ago. The lesson is that in the vast timescales of celestial mechanics, stability is never absolute. A two-moon Earth might appear eternal to those living under it, but its fate could be decided by the same inexorable physics that govern all worlds: gravity, momentum, and the quiet accumulation of change. Not all celestial tragedies arrive in a blaze of destruction. Some happen slowly, quietly, over spans of time so vast that no single generation would recognize the change. In the case of a two-moon Earth, one of the most plausible long-term instabilities would not be a dramatic collision, but rather the gradual drifting away of one moon until it slips free of Earth's gravity entirely. The cause would lie in the same tidal forces that, over billions of years, have been nudging our real moon farther from Earth at a rate of about 3.8 centimeters per year. With two moons, that outward drift would occur for both, but not necessarily at the same pace. Imagine the two moons locked in a delicate gravitational relationship, their orbital periods and distances finely tuned to avoid destructive encounters. Over time, tidal interactions with Earth transfer rotational energy into their orbits, pushing them outward. If one moon is lighter, it might drift faster. If it is farther out to begin with, it might be more susceptible to the Sun's competing gravitational influence. Eventually, it could reach a point where Earth's hold is no longer strong enough to keep it bound. Astronomers call this the Hill sphere, the region around a planet where its gravity dominates over the Sun's. Beyond this invisible boundary, a moon can be captured by the Sun as a new, small, planet-like body, or flung into an entirely new orbit through interactions with other planets. For the people of such a world, the early signs of this departure would be subtle. Careful observers might note that the receding moon rises and sets slightly later each year, and that its apparent size in the sky is shrinking. Over centuries, the change becomes undeniable. The moon grows fainter, its once bright disk diminished to a smaller coin of light. It no longer influences the tides as strongly, and its gravitational pull on Earth's axis weakens. Eventually, one night it fails to rise at all. In its place is a stretch of stars never before visible from that part of the world, and the sky feels strangely empty. The consequences for Earth would be immediate in some ways, gradual in others. The most obvious change would be in the tides. With only one moon remaining, the complex interference patterns that once defined the rise and fall of the seas would vanish. Tides would become simpler but weaker overall, unless the surviving moon were the larger and closer of the two. Coastal ecosystems that had adapted over millions of years to the erratic patterns of dual moon tides might suffer. Species that relied on extreme high tides for breeding, perhaps certain fish, amphibians, or shorebirds, could face population declines or extinction. Other species might flourish under the new, steadier conditions. Earth's axial stability would also be affected. The two moons together might have provided stronger resistance to long-term wobbles in the planet's tilt. With one gone, the stabilizing effect would decrease, leaving Earth more vulnerable to shifts in obliquity. Such changes might take thousands or millions of years to manifest, but they could lead to altered seasonal patterns, with shifts in climate zones, precipitation belts, and the extent of polar ice. For humanity, these changes could mean the slow redrawing of agricultural maps and the migration of populations toward more habitable regions. Culturally, the loss of a moon would be seismic. For as long as human memory reached back, the sky would have been defined by two luminous guardians. Their phases, alignments, and interplay would have been part of the calendar, the mythologies, the architecture, and the very identity of civilizations. To see one of them vanish into the void would be more than a physical change. It would be an existential shock. Poets might write of abandonment, of a sibling lost, of a broken celestial marriage. Prophets might interpret the disappearance as an omen, heralding disaster or transformation. For generations afterward, people might speak of the time before the empty sky. In some cultures, the departing moon might be followed, not in reality, but in the mind's eye. Stories could place it in the heavens as a wanderer among the stars, watching over Earth from afar. Some might believe it visits other worlds, bringing them the same gifts it once gave to Earth. Others might imagine it banished for some cosmic crime, destined never to return. The surviving moon might be cast as the lonely sentinel, its light tinged with melancholy. From a scientific perspective, the ejection of a moon would be a profound event to witness. Astronomers could track its changing orbit, measure its velocity as it crosses the Hill sphere, and determine whether it will become an independent body orbiting the Sun or be pulled into a more complex path influenced by other planets. If it passed close to Mars or Venus, for example, its trajectory could be bent into an entirely new orbit, perhaps even bringing it back near Earth on rare occasions. A ghostly reminder of what was lost. There is also the possibility that the ejected moon might not survive indefinitely. Freed from Earth's gravity, it could eventually collide with another planetary body, break apart in a close pass with a giant planet like Jupiter, or fall into the Sun after millions of years of orbital decay. Any such fate would be far beyond human timescales. but the knowledge of it could deepen the sense of impermanence. The lesson would be stark. Not even the most constant features of the sky are truly eternal. The departure of one moon could also set the stage for further instability. With the gravitational relationship between the moons broken, the surviving moon's orbit might shift in subtle ways, perhaps moving closer to Earth or becoming slightly more eccentric. Such changes could alter tidal patterns again, creating a period of adjustment for Earth's oceans, climates, and ecosystems. In extreme cases, if the remaining moon were nudged too close, it could eventually cross the Roche limit and disintegrate into a ring, leaving Earth with no moons at all. Over deep time, life on a one-moon Earth after such a loss would adapt to the new reality. The younger generations would know the old stories of the two moons, but the sight of the second in the sky would be only legend. Perhaps in the far future, if humanity mastered interplanetary travel, explorers might seek out the lost moon, finding it in its lonely orbit, untouched except by the slow processes of space weathering. They might land upon it, plant markers, and bring back samples, closing a chapter that began billions of years earlier in the fiery birth of the moons. Yet even in its absence, the vanished moon would leave an enduring mark. Its gravitational influence over the ages would have shaped coastlines, climates, and life in ways that could never be undone. The geological record would carry its signature in tidal sediments, fossil growth patterns, and the slow drift of Earth's spin rate. It would remain a part of Earth's story, not through its present presence, but through the echoes of what it once was. In the end, the ejection of a moon is not a sudden apocalypse, but a slow unraveling of a familiar order. It is a reminder that the cosmos is a place of movement, not permanence, and that even the grandest companions can drift away. For a two-moon Earth, it would be the moment when the dance became a solo, the harmony a single note. Beautiful still, but tinged forever with the memory of a duet that once lit the night. If Earth truly had two moons in the modern era, the study of our planetary system would be fundamentally different. Astronomy, planetary science, and space exploration would have grown up under the constant influence of this dual lunar reality. Every telescope built, every spacecraft launched, and every theoretical model constructed would have been shaped by the need to understand the complex gravitational ballet of the two moons. The result would be a body of knowledge richer in some areas, perhaps more accelerated in its development than what exists in our own single-moon world. From the earliest days of telescopic observation, astronomers would have been fascinated by the differences between the two moons. One might be larger and brighter, with vast lava plains and prominent craters. The other smaller, darker, perhaps more heavily pockmarked, or even irregular in shape. These physical differences would provide immediate clues to their origins, whether they formed together from the same giant impact debris, or whether one was captured later from elsewhere in the solar system. Centuries of drawing, mapping, and eventually photographing them would yield detailed records of their changing positions, allowing astronomers to track the long-term evolution of their orbits. Modern astrophysics would bring even greater precision to this task. Ground-based observatories equipped with adaptive optics could resolve features on both moon surfaces in remarkable detail, tracking changes caused by impacts, landslides, or volcanic activity, if any remained. Radio telescopes could bounce signals off their surfaces to measure distances with centimeter accuracy, allowing scientists to monitor the rate at which each moon drifts away from Earth. These data would be critical for understanding tidal interactions and predicting the moon's long-term stability. Space agencies would prioritize missions to both moons early in the space age. In our world, the Apollo program focused exclusively on the moon we have. In a two-moon Earth, missions might have been divided between the larger primary moon and the smaller secondary moon, perhaps even sending simultaneous expeditions to each. Robotic probes would map their terrain, analyze their compositions, and measure their gravitational fields. Differences in rock chemistry or isotopic composition could reveal whether the moons share a common origin, or if one was indeed a captured object from deep space. Lunar science would also feed directly into Earth science. With two moons exerting tidal forces, researchers would study how their combined influence affects ocean circulation, climate patterns, and Earth's rotation. This research would have practical applications in everything from predicting extreme tides to modeling long-term climate change. Satellite systems could be developed specifically to monitor the moon's gravitational pull on the oceans in real time, aiding navigation, fishing, and coastal management. Astrophysicists would run complex computer simulations to model the three-body problem of Earth and its moons. While the gravitational interactions of two moons can never be solved with a simple formula, numerical methods could produce highly accurate predictions of their motions for centuries into the future. Such models would be essential not only for science but for everyday applications. Spaceflight trajectories would need to account for the moon's positions and gravitational fields. Satellites in certain orbits could be perturbed by the moon's combined influence, requiring careful station-keeping. The International Space Station, in this world, might have been designed with a dual lunar view in mind, equipped with observation modules facing different directions to track both moons. Astronaut crews could take regular measurements, photograph eclipses involving one moon passing in front of the other, and test equipment for future missions to either body. The cultural impact of seeing two moons from orbit would be profound, and images of them together above Earth's curve might become iconic symbols of our place in the cosmos. Beyond Earth's immediate neighborhood, scientists would compare our system to other planets with multiple moons. Mars, for instance, has two small moons in our real solar system. In this alternate Earth, our own moons might be larger and more complex, offering unique insights into moon-moon interactions. Data from spacecraft visiting the moons of Jupiter and Saturn could be applied to understanding our own pair, refining theories of orbital resonance, capture dynamics, and tidal heating. The possibility of human settlements on both moons would also be a tantalizing frontier. The larger moon, with its more substantial gravity, might serve as a base for scientific research, resource extraction, or even tourism. The smaller moon, potentially with a lower escape velocity, could become a staging ground for missions deeper into the solar system. Engineers would study how the moon's different surface conditions, temperature extremes, radiation levels, and soil composition affect habitation design. Two distinct lunar environments would allow for comparative experiments that could speed up the development of off-world living technologies. International cooperation and competition would play out differently in this scenario. The geopolitical space race might involve not just Who can land on the moon first? But which moon will be claimed first? Scientific prestige would attach not only to first landings, but to the first crewed missions linking both moons in a single journey. Such achievements would demonstrate mastery of orbital mechanics and interlunar navigation, skills that could later be applied to missions to asteroids, Mars, or beyond. In the realm of public science, a two-moon Earth would capture the imagination in ways hard to overstate. Planetariums could offer shows simulating the complex interplay of their orbits. Schools might teach children to recognize different moon alignments in the night sky. Citizen scientist networks could track the moon's positions and contribute data to professional research. Amateur astronomers would enjoy twice the opportunities for lunar photography and study, with the added challenge of capturing rare events when one moon occults the other, or when both enter Earth's shadow during a double lunar eclipse. Environmental science would also benefit. The stronger and more complex tidal patterns caused by two moons would provide natural laboratories for studying coastal erosion, sediment transport, and the biology of intertidal zones. Satellite missions could map these changes in high resolution, feeding into models of how human-built infrastructure can adapt to or take advantage of lunar-driven ocean behavior. Finally, the philosophical and cultural implications of a two-moon Earth in the modern scientific age would be profound. The knowledge that our world is shaped by not one, but two large companions could influence our understanding of planetary habitability elsewhere in the universe. Astronomers might search for exoplanets with multiple moons, considering whether such systems are more likely to produce complex life. The sight of two moons from Earth's surface, both rising over a quiet ocean, their reflections dancing on the waves, would serve as a daily reminder that our home is part of a complex cosmic dance, one that is at once mathematically precise and poetically mysterious. In this way, modern science would not only measure and model the two moons, but integrate them deeply into our technology, our exploration, and our sense of identity as a species. Under their twin lights, humanity would chart a future shaped as much by curiosity as by necessity, forever aware that the sky above is more intricate and more beautiful than in the history we know. In a world where Earth has two moons, the possibilities for technological advancement and economic expansion would be greatly multiplied. Our single moon already represents a gateway to the wider solar system, a relatively close, stable, and accessible body whose resources and position make it invaluable for science and industry. With two moons, humanity would have not just one gateway, but two, each with its own distinct environment, composition, and orbital characteristics. The opportunities presented by this dual lunar system could accelerate the timeline of space development by decades, perhaps even centuries. The most obvious advantage would be in the realm of resource extraction. The larger moon might be rich in basaltic plains, with deposits of oxygen-bearing minerals, metals like titanium and aluminum, and perhaps pockets of water ice in permanently shadowed craters. The smaller moon, depending on its origin, could have an entirely different composition. If it formed from the same giant impact debris as the larger moon, it might share similar materials. But if it were a captured object from elsewhere in the solar system, it could be a treasure trove of unique resources. Imagine a captured carbonaceous body containing abundant volatiles, rare earth elements, or even organic compounds not commonly found on the larger moon. Mining operations could be established on both moons, with each specializing in different exports to Earth and to orbital manufacturing facilities. Materials extracted from the moons could be processed in situ or shipped to orbital construction yards, where they could be used to build satellites, space habitats, or deep space vehicles without the prohibitive cost of launching all materials from Earth's gravity well. The economic benefits of sourcing raw materials from space could fundamentally reshape industries ranging from energy to electronics. The existence of two moons would also offer unmatched opportunities for comparative research. Engineers and scientists could test technologies in two different low-gravity environments, adjusting for differences in surface composition, temperature variation, and radiation exposure. For example, a habitat designed for the larger moon might need to handle sharper day-night temperature swings, while one on the smaller moon might focus on mitigating higher radiation levels due to a thinner regolith or lack of magnetic shielding. Lessons learned on one could be applied to the other, and the variety of environments would help prepare humanity for eventual settlement of Mars, asteroids, or moons of the outer planets. Transportation between the moons themselves would become an important part of the space economy. Depending on their orbits, travel between them could be faster and more energy efficient than travel between Earth and Mars. This interlunar commerce might involve the transfer of resources, movement of crews, or even tourism. Spacecraft could shuttle between the moons using minimal fuel, especially if orbital mechanics allowed for gravitational assists from Earth. A network of depots and way stations could be established in strategic positions to support these journeys. One of the most revolutionary possibilities would be the creation of a permanent interlunar infrastructure, a chain of stations and facilities that link the two moons into a single operational system. These stations could serve as repair hubs, refueling points, or assembly yards for spacecraft headed deeper into the solar system. The existence of two moons might make it easier to establish stepping stone missions, in which spacecraft travel from Earth to one moon, refuel and resupply, then continue to the other moon before venturing farther out. This incremental approach could dramatically reduce the risk and cost of exploration beyond Earth orbit. From a technological standpoint, two moons could also act as testing grounds for planetary defense systems. In our world, the threat of asteroid impacts has driven interest in deflection technologies. In a two-moon Earth, these same systems could be refined by practice on the moons themselves. For example, by moving small boulders into controlled orbits for resource extraction or impact avoidance. Such techniques could one day protect Earth from genuine threats, and the dual-moon system would provide twice the opportunities to practice and perfect them. The moon's differing positions and orbits would also have value for communications and navigation infrastructure. Satellites placed in orbit around each moon could act as relays, providing global coverage for both lunar surfaces and supplementing Earth-based networks. In certain alignments, one moon could even serve as a communications outpost for spacecraft on the far side of the other, overcoming the radio blackout problem experienced during Apollo missions when the moon blocked signals to Earth. This layered network could be an essential backbone for a future space economy, enabling continuous coordination between operations spread across multiple celestial bodies. Economically, the presence of two moons could spark a competitive dynamic similar to the space race of the 20th century, but with far more sustained engagement. Nations or corporate entities might race to establish the first permanent settlement on each moon, or to develop the most profitable resource extraction system. The fact that the moons are distinct in composition and orbit would make them complementary targets rather than interchangeable ones, encouraging expansion to both rather than concentration on just one. Tourism, too, could play a significant role. The idea of visiting one moon is compelling enough. The ability to visit two, each with its own unique vistas and lighting conditions, could transform public enthusiasm for space travel. Imagine standing on the surface of the smaller moon, looking up to see both Earth and the larger moon dominating the sky. Or standing on the larger moon and watching the smaller moon rise and set against the distant Earth. These experiences could become iconic symbols of humanity's presence in space, inspiring future generations of explorers. There is also the strategic advantage. Control of both moons would provide unparalleled leverage in terms of Earth defense, orbital dominance, and access to deep space. Military or strategic installations on the moons could monitor space traffic, detect potential threats, and serve as launch points for missions beyond Earth orbit. The dual moon system could thus be both an economic engine and a geopolitical pivot point, shaping alliances, rivalries, and the balance of power on Earth. Perhaps most importantly, a two-moon Earth could accelerate humanity's psychological adaptation to being a multi-world species. With two distinct but accessible destinations in the night sky, the idea of living and working beyond Earth would feel less extraordinary and more routine. This mental shift, from seeing space as a distant frontier to seeing it as an extension of our daily sphere, could be the most transformative impact of all. Once that shift occurs, the leap from the moons to Mars, asteroids, and beyond becomes far easier to imagine and far harder to resist. In this way, the two moons would not merely shape the economics of space, they would shape the trajectory of human civilization itself. The resources, opportunities, and inspiration they offer could propel humanity into an age of exploration and development unmatched in history. An age lit not by the pale glow of one companion, but by the twin beacons that have always shared our sky. If humanity were born under the light of two moons, one of the greatest scientific challenges and fascinations would be to understand the intricate mechanics of their orbits and the ways they influence Earth. In the modern era, this effort would inevitably be driven by the power of supercomputers. These machines, capable of performing trillions of calculations per second, would allow scientists to recreate billions of years of celestial history in compressed time, to model the present state of the system with unprecedented precision, and to project its evolution far into the future. The first task in such simulations would be to reconstruct the moon's origins. If both moons formed in the aftermath of a giant impact, such as the hypothesized collision between Earth and Theia, scientists could use smoothed particle hydrodynamics (SPH) simulations to model how molten debris coalesced into multiple bodies. These simulations would take into account the density, temperature, and composition of the impact material, as well as the velocity and angle of the collision. By running thousands of variations with slightly different initial conditions, researchers could identify the scenarios most likely to produce two large, long-lived moons. If one moon were suspected to be a captured object, the simulations would change in character. Astronomers would model close encounters between Earth and passing asteroids or dwarf planets, calculating the precise conditions under which Earth's gravity, perhaps aided by the presence of the existing moon, could capture another body into a stable orbit. Such models would also examine the long-term stability of these captures, identifying whether they could survive for billions of years or would likely end in ejection or collision. Once the origin scenarios were understood, scientists could shift focus to the present-day system. Here, the challenge would be to solve a variant of the three-body problem: the gravitational interactions between Earth, Moon A, and Moon B, with the Sun acting as a powerful fourth participant in the dance. While the equations of motion for such a system are well known, their solutions are chaotic over long timescales, meaning small uncertainties in initial conditions can lead to vastly different outcomes. Supercomputers would be essential to track these interactions with high precision, using n-body integrators to step forward in time while minimizing cumulative errors. These simulations would allow scientists to map the system's phase space, the vast range of possible orbital configurations, and identify the regions where the moon's orbits are stable. They could test the effects of different resonances, such as a 2:1 or 3.2 orbital ratio, to see which produce the least perturbation over millions of years. In unstable configurations, the models could track how quickly instability grows, revealing whether trouble might arise in thousands, millions, or billions of years. The simulations would not be limited to orbital mechanics. They would also model the moon's gravitational influence on Earth's tides, rotation, and axial tilt. Using coupled ocean-atmosphere models, scientists could explore how dual moon tides might alter global circulation patterns, influence climate zones, and affect the distribution of nutrients in the oceans. By running simulations over long timescales, they could investigate whether the two moons help stabilize Earth's climate more effectively than a single moon, or if they instead introduce periodic disruptions that could affect the biosphere. One particularly ambitious set of simulations would integrate geology into the picture. By coupling orbital models with tectonic and volcanic models, researchers could study whether the tidal forces from two moons might increase the frequency of earthquakes or volcanic eruptions. They could examine how these effects vary with different moon alignments, producing predictive tidal stress maps of the planet. In a two-moon Earth, such forecasts could be vital for hazard planning in tectonically active regions. Beyond the present, simulations would be used to forecast the future of the system. Here, the focus would be on tidal evolution, the gradual outward drift of the moons due to the transfer of Earth's rotational energy into their orbital motion. Scientists could model whether the moon's drift rates would cause them to approach dangerous resonances, to eventually collide, or to part ways as one is ejected from the system. These models would be run for time horizons far beyond the lifespan of the Sun, showing the ultimate fate of the moons in a universe that will long outlast our planet. Because the behavior of such a system can be sensitive to tiny uncertainties, simulations would often be run in ensembles, thousands or millions of slightly different scenarios, to produce statistical forecasts. Instead of predicting a single deterministic outcome, scientists could estimate probabilities. A 70% chance that the system remains stable for the next billion years, a 20% chance of collision within 500 million years, and a 10% chance of ejection events. These probabilities would guide not just scientific understanding, but perhaps cultural and philosophical reflection on the impermanence of celestial order. Practical applications would emerge as well. Space agencies could use near-term simulations to plan missions, choosing launch windows when the moon's relative positions minimize fuel costs. Telecommunications companies could use models of the moon's positions to optimize satellite coverage. Coastal planners could rely on tide predictions that account for both moons' influence, and shipping companies could adjust schedules to avoid the strongest tidal surges. The simulations themselves would evolve alongside technology. As computing power increased, models could incorporate ever more detail: the gravitational pull of large asteroids, the deformation of Earth and the moons due to tidal forces, even relativistic effects from the sun's gravity. Advances in machine learning could allow neural networks to emulate complex simulations, generating accurate forecasts in a fraction of the time. This could make detailed two-moon predictions available to anyone with a handheld device, democratizing access to what was once the domain of elite scientific institutions. For the public, visualizations derived from these simulations would be as inspiring as they are informative. Imagine standing in a planetarium and watching a time-lapse of the two moons drifting through their cycles, their orbits subtly shifting over millennia. Or exploring an interactive model on a computer, fast-forwarding millions of years to see how alignments change, eclipses occur, or, in rare cases, catastrophes unfold. Such tools could transform the abstract mathematics of orbital mechanics into vivid experiences that connect people emotionally to the sky above. Ultimately, the purpose of simulating a two-moon Earth would not be just to predict its mechanics, but to understand its place in the broader context of planetary systems. By comparing our model results to observations of exoplanets and their moons, scientists could test whether multi-moon systems are common in the galaxy, and whether they tend to foster stable climates conducive to life. In this way, the study of our own dual-moon system would become a stepping stone toward understanding the habitability of worlds far beyond our reach. The two moons would thus be more than subjects of curiosity. They would be dynamic laboratories in which the interplay of gravity, geology, climate, and life could be studied as nowhere else. In the digital landscapes of supercomputer simulations, we would be able to witness their birth, trace their intricate dance through billions of years, and glimpse their eventual fate. And in doing so, we would not just be exploring the mechanics of a hypothetical sky. We would be deepening our knowledge of the forces that shape worlds, the fragility of stability, and the grand patterns that govern the cosmos. Speculation about a second moon is not confined to the realm of science fiction or thought experiments. Even in our real single-moon history, there have been scientific proposals, some serious, others fringe, that Earth may once have had additional companions. In this imagined two-moon Earth, the question would be inverted. Could such a world leave unmistakable traces in its rocks, sediments, and the records of its skies, even after one moon had been lost? The search for evidence would begin with geology. Earth's tides are intimately tied to the gravitational pull of its moon, and the rhythms of those tides leave marks in sedimentary layers. Over millions of years, tidal deposits accumulate in patterns that reflect the timing and strength of tidal cycles. In our real world, ancient tidal rhythmites, layered sediments recording high and low tides, have been used to estimate the length of Earth's day hundreds of millions of years ago. On a two-moon Earth, these rhythmites might reveal far more complex patterns. Interference beats where the two moons' tidal influences overlapped, cycles of unusually high or unusually low tides when both moons aligned, and subtle shifts as their orbital relationships evolved. Geologists would scour ancient coastal deposits for these patterns, seeking repeating sequences that could only be explained by dual lunar tides. If the second moon had been lost in the deep past, the transition from dual to single tidal signals could be pinpointed in the rock record, marking the era of its departure. Such a discovery would be akin to finding a fossilized footprint of a vanished celestial body. Beyond tidal sediments, scientists could look for evidence in the growth patterns of ancient organisms. Certain corals, mollusks, and stromatolites grow in daily and seasonal cycles, leaving microscopic bands in their skeletons. In our world, these growth bands reveal that days were shorter in the past, due to Earth's faster rotation. On a two-moon Earth, the growth bands might carry the imprint of more complex tidal rhythms, or even slight wobbles in climate linked to the gravitational effects of two moons. These biological records could act as living calendars, capturing the sky's influence across deep time. Astronomy would provide another avenue for the search. If a second moon had once existed and been lost, either through collision, ejection, or disintegration, traces of its demise might remain in space. For example, a collision could have left a ring of debris that slowly fell to Earth or the remaining moon, creating an identifiable layer of impact ejecta in geological strata. If the moon was ejected into the solar system, it might still be orbiting the Sun today as an asteroid-like object, with an unusual composition matching our own moon's geology. Planetary dynamicists could model the probable paths of such an ejected moon, identifying regions of the solar system where it might be found. Large telescopic surveys could then search for candidate objects, analyzing their spectra for a telltale match to lunar rocks. Even a partial match, such as oxygen isotope ratios identical to those of Earth and its moon, could point to a shared origin, suggesting the object was once part of our neighborhood. In the case of a disintegration event, evidence might be more subtle. Fragments of the destroyed moon could have impacted both Earth and the surviving moon, leaving clusters of craters of similar age and composition. High-resolution mapping of the remaining moon's surface could identify such crater families, while Earth's own ancient impact basins could be redated to look for matches. This type of forensic work, linking impact events across worlds, would be painstaking but potentially definitive. Another line of evidence might come from the dynamics of the surviving moon's orbit. If one moon had been lost in a violent event, the gravitational kick to the remaining moon could have altered its orbit in ways that are still detectable. Precise laser-ranging measurements, already used in our real world to track the moon's distance to the millimeter, could reveal anomalies inconsistent with a smooth tidal evolution. These anomalies, when combined with orbital simulations, could hint at a past gravitational upheaval. Historical records could also hold clues, though only for events in the recent past on astronomical timescales. In our actual history, ancient astronomers documented eclipses, planetary alignments, and other celestial phenomena. In a two-moon world, The existence of both moons would be a central feature of such records. If one were lost within the span of human civilization, myths, stories, and even early astronomical sketches could preserve memories of its disappearance. Cultures might speak of a vanishing light, or the day the second guardian left the sky. While poetic, these accounts could be cross-referenced with geological or astronomical data to narrow down the timing of the loss. The absence of direct evidence would not necessarily rule out the past existence of a second moon. Planetary systems are dynamic, and smaller bodies are more easily removed without leaving obvious traces. A captured moon in a wide orbit, for instance, might have been lost without a single catastrophic event, simply drifting away under the influence of the sun's gravity until it was gone. In such a case, the only evidence might be statistical. The fact that multiple moons are common around other planets, and Earth's solitary moon status is somewhat unusual. In this alternate history, where two moons have been constant for billions of years, scientists might reverse the question. What signs could future geologists and astronomers detect if one were to be lost tomorrow? They would likely focus on the very same markers: tidal rhythmites, biological growth bands, crater patterns, debris signatures, and orbital anomalies. The knowledge gained from such a loss would not only explain the system's past, but provide insight into the fragility of multi-moon arrangements across the cosmos. This search for evidence would resonate beyond pure science. The idea that a celestial companion could vanish, leaving only faint traces in stone and story, speaks to the impermanence of even the most seemingly eternal features of our world. Just as mountain ranges erode and seas advance and retreat, the sky itself can change. A reminder that our place in the universe is part of an ongoing, restless process. For a two-moon Earth, the loss of one would be both an astronomical event and a cultural watershed, remembered for as long as memory lasts, and then forgotten until rediscovered in the patient work of science. Ultimately, the investigation into whether Earth once had a second moon would be a multidisciplinary quest, uniting geologists, astronomers, paleontologists, and historians. It would require tools that reach from the microscopic scale of coral growth bands to the cosmic sweep of orbital simulations. And while the definitive answer might remain elusive, the process itself, the attempt to read the sky's lost chapters from the pages of stone and light, would deepen our understanding of how worlds evolve, how companions are gained and lost, and how the marks of those changes endure long after the events themselves have passed into silence. If Earth had always been accompanied by two moons, the story of human culture would be written under their twin glow. From the earliest flickers of symbolic thought, the sight of not one but two great disks crossing the heavens would have become one of the most defining features of the human experience. Just as the phases of a single moon in our real history inspired calendars, rituals, and myths, the dual lunar sky of this alternate Earth would have layered meaning upon meaning, generating a tapestry of beliefs and artistic traditions unlike anything we have known. In the earliest human societies, the two moons would have been powerful markers of time. Each moon would have its own cycle of waxing and waning, and the interplay between the two cycles would create complex patterns in the night sky. Early timekeepers might have used these patterns to divide the year into a nested system of lesser and greater months. The alignment of the moons, when both are full or both are new, or when one is waxing as the other wanes, could have been seen as omens, each combination associated with specific meanings for planting, hunting, or warfare. Mythologies would have blossomed from these observations. In some cultures, the moons might have been siblings, one older, brighter, and more stable, the other younger, dimmer, and more restless in its path. Their periodic alignments could be framed as family reunions or moments of celestial harmony, while their separations could symbolize distance, exile, or the inevitability of change. Other cultures might interpret the two moons as eternal lovers, locked in a slow dance across the heavens, sometimes near enough to touch in the sky, sometimes drifting far apart, but always bound by invisible ties. The dual eclipses possible in such a world would have been especially dramatic. A lunar eclipse involving one moon while the other still shone brightly would have been a perplexing sight to early sky watchers, perhaps interpreted as one moon falling ill while the other kept watch. On rare occasions when both moons entered Earth's shadow together, plunging the night into an uncanny darkness, the event could have been seen as a cosmic crisis, requiring rituals to restore balance. Solar eclipses would also take on new complexity, with either moon capable of covering the sun and, on extremely rare alignments, both crossing the sun in sequence or even simultaneously, creating a double eclipse that would be remembered for generations. Artistic traditions would reflect the constant presence of two celestial companions. In Paleolithic caves, alongside images of animals and hunting scenes, there might be depictions of two circles side by side or overlapping, a simple but enduring symbol of the night sky. As civilizations advanced, the motif could evolve into architectural designs, temples with twin towers aligned to the rising points of each moon, or ceremonial spaces oriented to key alignments in their cycles. In some cultures, jewelry might feature paired gemstones to represent the moons, worn as talismans for balance and duality. Philosophy and religion would also be deeply shaped by this sky. The concept of duality, two forces complementing or opposing each other, would be reinforced by nightly observation. Where our own history often frames existence in terms of light versus dark, good versus evil, a two-moon world might develop more nuanced frameworks. Harmony versus discord, unity versus separation, or cyclical cooperation versus cyclical conflict. These concepts could permeate law, ethics, and cosmology. In societies where one moon appears larger or brighter than the other, hierarchical interpretations might emerge. One moon as the ruler, the other as the servant, or one as the parent, the other as the child. Conversely, cultures valuing equality might emphasize the moon's mutual dependence, seeing in their dance a metaphor for human relationships, governance, or the balance between genders. Literature and poetry would draw heavily from lunar imagery. Lovers might swear oaths beneath the twin moons, while tales of heroes could feature quests to reconcile the moons when they drift apart, or to protect one from an imagined danger. Seasonal festivals might coincide with especially beautiful alignments. For example, when both moons rise together at twilight, their combined light silvering the land in a way no single moon could. In urban centers, the dual moons would shape daily life. Architects might design cities to take advantage of their combined illumination, reducing dependence on torches or lamps. Nighttime navigation, both on land and at sea, would incorporate the moon's positions, with sailors using the geometry of their separation to confirm their course. In the arts, painters and sculptors could explore the emotional contrasts between nights when both moons are high and bright, casting crisp shadows, and those when they are far apart or in different phases, creating softer, more complex lightscapes. Over centuries, as astronomy matured, the moon's motions would inspire philosophical debates about determinism and chance. The predictable patterns of their orbits would seem to suggest an ordered cosmos, yet their complex interplay, especially if one moon's orbit were slightly inclined or eccentric, would also demonstrate the beauty of irregularity within order. This tension could influence not just science, but broader worldviews, encouraging cultures to embrace both precision and adaptability. Religious calendars could grow extraordinarily sophisticated. In some traditions, holy days might require the moons to be in a specific geometric arrangement, such as forming an equilateral triangle with a particular star. Pilgrims might travel great distances to witness these alignments at sacred sites. The construction of monumental observatories, akin to Stonehenge or Chichen Itza in our world, could be even more common, with alignments carefully tuned to mark rare double moon events occurring only once in a human lifetime. In the age of exploration, the two moons would become symbols of humanity's connection to the broader cosmos. Flags of maritime nations might display them as navigational guides, while empires could claim dominion under the light of both moons, using their imagery in seals and coinage. Explorers crossing uncharted oceans could measure their progress not just by the stars, but by the changing dance of the moons, their motions reassuring in the midst of uncertainty. Even in modern times, the psychological and cultural resonance of two moons would remain potent. Photographs of their conjunctions could inspire global moments of awe, much as images of Earth from space have done in our reality. Popular culture, films, novels, music, would draw on their symbolism to evoke themes of connection, separation, and cosmic wonder. Philosophers might still debate whether the presence of two moons has shaped human identity in ways we cannot fully disentangle, subtly influencing how we think about balance, relationships, and the cycles of change. In this alternate history, the two moons would not just be astronomical objects. They would be constant companions in humanity's journey, woven into the language, symbols, and collective imagination of countless cultures. Their presence would remind each generation that the world is part of a greater cosmic pattern, a dance not of solitary motion, but of shared paths, recurring meetings, and graceful separations. Under their twin light, humanity would look upward not in loneliness, but in the company of two eternal guides. From the moment life first looked skyward, the moons would have been there, steadfast and familiar, yet ever-changing. Through billions of years of planetary evolution, through the rise and fall of oceans, continents, and civilizations, they would have traced their slow dance around our shared home. In this imagined world of two moons, they would not merely be background ornaments in the night. They would be constant presences, as much a part of the Earth's identity as the continents or the seas. The journey to understand such a world would begin in curiosity and end in a kind of reverence. Scientists would study the moons for their origins, building simulations that replayed the cataclysmic events of the early solar system. They would model the tidal forces shaping the planet's coastlines, the shifts in climate driven by their combined gravitational pull, and the intricate orbital mechanics keeping them bound in their perpetual rhythm. Each discovery would deepen our appreciation for the delicate stability of this dual moon system and for the remarkable balance that allows life to flourish beneath it. Historians and archaeologists would uncover evidence of the moon's influence in every culture's story. In carvings on temple walls, in the alignment of ancient monuments, in the language of myths and prayers, they would find the imprint of a sky ruled by two lights. Anthropologists would trace how the moons shaped human perception of time, how their phases guided agriculture, and how their rare alignments became moments of collective wonder and ritual significance. The moons would be mirrors, reflecting not only sunlight, but the human need to create meaning from the patterns of the cosmos. Philosophers, too, would turn their attention upward. Some might see in the two moons a metaphor for the balance of opposites, light and shadow, change and constancy, individuality and relationship. Others might see them as a lesson in complexity, a reminder that stability in nature often arises not from simplicity, but from the interplay of multiple forces. Their nightly presence would invite reflection on humanity's place in the universe, a small, brief flicker in the vast cosmic theater, yet one accompanied by companions that have endured for eons. In the practical realm, the two moons would have driven innovation. Their tides would have shaped trade routes and fishing grounds, their light aiding navigation long before the compass was invented. The drive to predict their motions with precision would have fueled the development of mathematics and astronomy. In the modern era, they would be stepping stones into space, resource-rich worlds that could support humanity's expansion beyond Earth. Spacecraft would shuttle between them, science stations would dot their surfaces, and their differing compositions would provide the raw materials for new technologies. The twin moons would be both laboratories and gateways, places where humanity could test itself against the challenges of living beyond its home planet. The cultural resonance of the moons would persist, even as technology advanced. Poets would still write of lovers meeting beneath the twin lights. Artists would still paint their rare conjunctions, and photographers would still wait for hours to capture the perfect moment when both rise together over a mountain ridge or an ocean horizon. Cities might host festivals timed to their most striking alignments, celebrating the cycles that link the present day to the deep past. Even in the age of artificial illumination, people would still look up at night and feel something ancient stir within them. This imagined dual-moon Earth would also remind us of the fragility of cosmic arrangements. In simulations, scientists would see how easily such systems could destabilize, how a slight change in mass, velocity, or distance could lead to collision or ejection. That knowledge would carry a subtle undercurrent of humility. The moons might feel eternal, but like all celestial configurations, they would have a finite lifespan. One day, far in the future, tidal forces could push one outward until it escapes Earth's grasp, or pull the other inward until it shatters. In that knowledge lies a lesson. Even the most enduring companions in the night sky are subject to change. Perhaps this awareness would foster a deeper connection between humanity and its moons. Knowing that their beauty is not forever might inspire a greater desire to explore them, to document them, to weave them more tightly into the story of our species. The moons would be more than scientific curiosities. They would be part of the heritage of life on Earth, their light having fallen on every creature that has ever walked, swum, or flown here. And if, in some distant epoch, one moon were lost, the event would be profound. Its absence would not only alter tides and climate, but reshape culture and identity. Songs, myths, and traditions tied to the lost moon would take on a tone of longing. Generations born afterward would know the stories, but never the sight of the missing light. The surviving moon would carry a heavier symbolic weight, its phases watched with both gratitude and melancholy. In the rocks and the records, future scientists would find the evidence and piece together the story, preserving the memory of the vanished companion. Yet as long as both remained, the night sky would offer a constant reminder of partnership, not a solitary path through the cosmos, but a shared one. To stand on a quiet shore and watch both moons rise together would be to feel the vastness of time and the intimacy of the present moment all at once. It would be to recognize that we are part of a system, Earth and its moons, that is itself part of a larger, unfolding universe. In the end, the story of a two-moon Earth is not just about celestial mechanics, tides, or geological history. It is about the human impulse to look upward and wonder, to find meaning in the lights that move across the darkness, to build science and art in response to what we see. The moons, real or imagined, are not just features of the sky. They are catalysts for curiosity, connection, and creativity. And so, if we lived in such a world, the question, what if Earth had a second moon, would not be merely hypothetical. It would be part of our daily experience, woven into the rhythm of life as surely as sunrise and sunset. The answer would be written in the way we measured time, in the architecture of our cities, in the myths we told our children, and in the science that carried us beyond our home planet. It would be an answer both scientific and poetic, grounded in the laws of physics, yet alive in the language of human imagination. Beneath the light of two moons, humanity's gaze would always return to the sky, finding in it both a reflection of ourselves and a reminder of the greater patterns of which we are a part. And perhaps, in that constant act of looking upward, we would come to understand not only our place in the universe, but the universe's place within us.